Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the invisible rain that falls continuously upon our world. A rain made not of water, but of stardust and ancient memories from the depths of space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Above the atmosphere, beyond the reach of clouds and weather, another kind of precipitation takes place. Every second of every day, thousands upon thousands of microscopic particles drift down through the vacuum of space, each one no larger than a grain of pollen, each one carrying within its crystalline structure the chemical signature of worlds beyond Earth. They arrive without fanfare, without the dramatic streak of shooting stars, settling instead with the patient inevitability of geological time itself. These cosmic visitors have been falling for 4.5 billion years, a steady accumulation that began when Earth was still molten and continues now as satellites orbit overhead and cities glow beneath the stars. Scientists estimate that between 15 and 300 tons of this extraterrestrial material settles onto our planet each day. The uncertainty itself a reminder of how much mystery still surrounds this ancient process. The particles arrive as silently as snowflakes, each one a messenger from the outer reaches of the solar system. The very air carries their presence. High in the stratosphere, specialized aircraft equipped with aerogel collectors sweep through the thin atmosphere, gathering these visitors before they can be contaminated by earthly elements. The collection plates return filled with particles so small they exist at the boundary between matter and emptiness. Specks that formed in the stellar nurseries of distant galaxies, travelled for eons through interstellar space, and finally found their way to our small corner of the cosmic dance. Some of these particles formed in the cooling gas around dying stars, condensing from stellar winds that carried the nuclear ashes of supernovae across light years of emptiness. Others crystallized in the outer reaches of our own solar system, where temperatures hover just above absolute zero and sunlight arrives as barely more than starlight. A few bear the chemical signatures of processes that occurred before the sun ignited, relics from the molecular cloud that collapsed to form our entire solar system. In laboratory clean rooms around the world, researchers examine these microscopic travelers under electron microscopes, revealing structures more delicate than butterfly wings, yet tough enough to survive journeys spanning millions of kilometers and millions of years. Some particles show the glassy sheen of rapid cooling in the vacuum of space. Others display the layered architecture of slow crystallization in the frigid darkness between worlds. A few bear the scars of cosmic ray bombardment, their surfaces pitted by high-energy particles streaming from distant stars. The examination process itself requires extraordinary patience. Each particle must be extracted from its collector using techniques borrowed from microsurgery, manipulated with tools so fine they can move individual atoms. Under the electron microscope's beam, these cosmic grains reveal their secrets. Mineral structures unknown on Earth, isotopic ratios that tell stories of stellar evolution, organic compounds that formed in the interstellar medium billions of years before life emerged from Earth's primordial oceans. The irony rests in plain sight. While humans have spent centuries dreaming of touching the stars have been touching us all along, settling quietly into ocean sediments and polar ice, accumulating in the corners of gutters and on the surfaces of leaves. Every breath contains atoms that once drifted free in the cosmic wind, Every handful of soil holds fragments of asteroids that formed when the solar system was young. The dust that settles on windowsills contains, in microscopic quantities, the substance of comets and the debris of worlds that never quite became planets. These particles carry within them isotopic ratios unknown on Earth, signatures of nuclear processes that occurred in stellar cores billions of years ago, markers of chemical reactions that took place in the outer reaches of the solar nebula before planets had names or observers to name them. Each microscopic grain represents a data point in the vast experiment of cosmic evolution, a single verse in the longer poem of matter and time. The scientific instruments designed to study these visitors push against the limits of measurement itself. Mass spectrometers sensitive enough to detect individual atoms pass the chemical composition of grains smaller than bacteria. X-ray diffraction patterns reveal crystal structures that formed under conditions impossible to recreate in terrestrial laboratories. Scanning electron microscopes map surface features measured in nanometers, creating portraits of textures sculpted by radiation pressure and solar wind over geological ages. Yet for all the sophisticated analysis, perhaps the most remarkable aspect of this cosmic precipitation lies in its quiet persistence. Right now, as you listen to these words, particles that began their journey when dinosaurs ruled the Earth are settling onto the planet's surface. Others that started their descent during the last ice age are still drifting through the outer atmosphere, their arrival delayed by atmospheric dynamics and electromagnetic fields. The particles themselves seem almost impossibly small to carry such profound implications. A typical interplanetary dust grain measures between 1 and 100 micrometers across, dimensions that place them in the realm of bacteria and pollen. Invisible to the naked eye, yet massive enough to carry within their structure the memory of cosmic processes spanning billions of years. They exist at the intersection of the infinitesimal and the infinite, bridges between the human scale of experience and the vast scales of space and time. Tonight, as darkness spreads across continents and stars emerge in the deepening sky, approximately 40,000 of these cosmic visitors will settle onto each square kilometre of Earth's surface. They fall onto mountains and cities, forests and deserts, adding their infinitesimal weight to a planet that has been growing heavier, grain by grain, since the beginning. Only took 4 billion years to build a library written in dust, and the writing continues still, letter by microscopic letter, in a language older than life itself. The collection continues in perfect silence, a cosmic punctuation that marks the passage of deep time with the gentle accumulation of stardust on stone. Each particle a period at the end of a sentence written in the motion of worlds around distant suns. Each grain a reminder that the universe is not empty space punctuated by occasional matter, but rather a continuous fabric of connection spanning the distance between atoms and galaxies. In the hours before dawn, when darkness reaches its deepest point and city lights dim to their lowest glow, a faint luminescence begins to emerge along the eastern horizon. This is not the first blush of sunrise, but something far more ancient and mysterious. A ghostly pyramid of light that stretches upward from the horizon. Following the path the sun will trace across the sky hours later. Astronomers call this phenomenon the zodiacal light, and for centuries it remained one of the most beautiful mysteries visible to the naked eye. The light appears so delicate that even the smallest amount of atmospheric haze or light pollution can erase it completely from view. In desert locations far from cities, where the air carries no moisture and no artificial illumination drowns the subtle glow, the zodiacal light reveals itself as a pale, tapering cone that can extend halfway to the zenith. Ancient Persian astronomers called it the false dawn, mistaking its gentle radiance for the approaching sunrise. Medieval Islamic scholars documented its appearance with careful precision. noting how it shifted position with the seasons and varied in brightness throughout the year. What these early observers could not have known is that they were witnessing sunlight scattered by a vast disk of debris that extends throughout the inner solar system, the same cosmic dust that settles continuously onto Earth's surface. This interplanetary medium represents the accumulated detritus of billions of years of solar system evolution, a slowly rotating carousel of particles that follows the same general plane as the planets themselves. The zodiacal light is nothing more than sunlight reflecting off countless microscopic grains, each one too small to see individually but collectively numerous enough to paint the pre-dawn sky with their scattered radiance. The disk itself extends from well inside Mercury's orbit all the way beyond Mars, with the greatest concentration of particles lying in the asteroid belt and the inner regions where Earth orbits. Scientists estimate that this debris field contains somewhere between 10 to the 13th and 10 to the 19th kilograms of material, a mass equivalent to a small asteroid distributed across billions of cubic kilometers of space. The precise number remains uncertain because the particles exist at densities so low they challenge the fundamental definition of matter itself. Each particle in this vast collection has its own story of origin and wandering. Some formed in the outer reaches of the solar system, where comets shed their substance as they approach the sun's warmth. Others represent the ground-down remains of asteroid collisions, fragments of fragments that have been pulverized and repulverized over geological time until they exist as little more than organized clouds of silicon and iron. A few carry within their crystal matrices the chemical signatures of interstellar space, visitors from other solar systems that have been captured by our sun's gravitational influence. The zodiacal light varies in intensity throughout the year, growing brighter during certain seasons as Earth's orbit carries it through denser regions of the debris field. In the autumn months, when the ecliptic plane makes its steepest angle with the western horizon after sunset, the glow can become prominent enough to cast faint shadows in locations with perfectly dark skies. Spring brings the most spectacular displays of the morning zodiacal light, when the pre-dawn hours reveal the full extent of the cosmic dust clouds stretching along the path of the planets. Modern space missions have sailed directly through this debris field, their instruments recording the constant patter of microscopic impacts against their hulls and solar panels. The Pioneer and Voyager spacecraft, during their journeys to the outer planets, documented the gradual decrease in particle density as they travelled beyond Mars. Their dust detectors registered impacts from grains so small that individual collisions released energy measured in fractions of a joule, yet so numerous that the cumulative bombardment slowly eroded the spacecraft's surfaces over years of interplanetary travel. The Ulysses mission, launched to study the Sun's polar regions, provided the first comprehensive map of dust density throughout the inner solar system. Its instruments revealed that the debris field is not uniform but contains streams and clusters that correspond to the orbital paths of defunct comets. These gravitational sculptures in dust mark the passage of ancient visitors that have long since exhausted their volatile materials, leaving behind only the rocky skeletons of their passage preserved in patterns of drifting particles. What strikes researchers as particularly remarkable is the dynamic nature of this seemingly static phenomenon. The zodiacal light appears constant from Earth's perspective, a reliable feature that photographers can plan their expeditions around. Yet the individual particles creating the glow are in constant motion. Computer simulations reveal that a typical dust grain in the inner solar system follows a complex trajectory influenced by solar radiation pressure, gravitational perturbations from the planets, and electromagnetic forces generated by the Sun's magnetic field. The Poynting-Robertson effect, first described in the early 20th century, ensures that these particles cannot maintain stable orbits indefinitely. Sunlight carries momentum, and when photons strike a dust grain and are absorbed or re-radiated, They impart a tiny but persistent force that gradually slows the particle's orbital motion over time scales measured in thousands to millions of years. This cosmic friction causes particles to spiral slowly inward toward the Sun, where they are eventually vaporized in the solar atmosphere. This process of orbital decay means that the zodiacal cloud requires constant replenishment to maintain its observed density. The source of this renewal represents one of the ongoing puzzles in planetary science. Comets contribute material each time they pass through the inner solar system, shedding dust and gas that eventually settles into the general debris field. Asteroid collisions generate fresh clouds of fragments that gradually disperse along orbital paths. Even the Moon contributes microscopic ejecta when meteoroids strike its airless surface, launching plumes of lunar material into interplanetary space. Recent observations from the Spitzer Space Telescope and other infrared observatories have revealed additional structure within the zodiacal cloud that was invisible to earlier ground-based studies. These instruments detect thermal emission from dust grains warmed by sunlight, creating maps of particle density that show features resembling spiral arms and ring structures. Some of these patterns appear to correlate with the orbital resonances of Jupiter and other giant planets, suggesting that gravitational influences shape the distribution of debris in ways that are still being understood. The very faintness of the zodiacal light serves as a reminder of how empty space actually is between the planets. Despite containing trillions upon trillions of particles, the interplanetary medium maintains a density so low that a spacecraft can travel for months without encountering a single grain large enough to damage its instruments. The light we see represents the collective reflection from a vast number of objects, each smaller than the width of a human hair, distributed across a volume that could contain thousands of Earths. Tonight, as the zodiacal light begins its slow emergence above the eastern horizon, it illuminates a debris field that has been accumulating for nearly as long as the solar system has existed. The gentle glow marks the presence of cosmic archaeology written in dust, a museum of solar system history that drifts through space in microscopic fragments. Each grain an artifact from the era when planets were still forming and the architecture of the solar system remained unfinished. It only took 5 billion years to build a monument made of emptiness and starlight, and still the ancient light continues to rise, revealing the presence of absence, the substance of space itself made visible through the patient accumulation of cosmic dust across the immeasurable distances between worlds. The individual particles that create the zodiacal light exist at a scale that challenges human comprehension, occupying the liminal space between the visible and the invisible, between matter and void. A typical interplanetary dust grain measures between 1 and 100 micrometers in diameter, dimensions that place these cosmic travelers in the same size range as bacteria, pollen grains, and the finest particles of clay. To appreciate their true scale, imagine a grain of table salt reduced to the size of a period on this page, then reduced again by the same proportion. Even then, the comparison fails to capture the extraordinary delicacy of these structures, which have survived journeys measured not in kilometers, but in astronomical units, not in days, but in geological epochs. Each particle represents a marvel of cosmic engineering, a microscopic spacecraft designed by the physics of space itself to survive conditions that would instantly destroy any human-made object. The vacuum of interplanetary space subjects these grains to temperature variations that swing from hundreds of degrees above absolute zero when illuminated by direct sunlight to the bitter cold of deep space when they pass into shadow. Cosmic radiation bathes them in high-energy particles that can alter their atomic structure at the most fundamental level. Solar wind, the constant stream of charged particles flowing outward from the sun, bombards their surfaces with ions travelling at velocities measured in hundreds of kilometers per second. Yet somehow, these microscopic structures endure. Scanning electron microscope images reveal surfaces sculpted by eons of cosmic weathering. displaying textures that range from smooth glassy coatings to intricate crystalline architectures. Some particles show evidence of multiple thermal cycles, their surfaces bearing the scars of repeated heating and cooling as their orbits carried them closer to and farther from the Sun. Others display the characteristic pitting caused by micrometeorite bombardment, their surfaces cratered by impact from particles even smaller than themselves. The journey that brings these grains to Earth begins at distances that strain the imagination. Some particles originate in the Kuiper Belt, that vast ring of icy bodies that extends from Neptune's orbit to nearly twice that distance from the Sun. Others emerge from the even more distant Oort cloud, a spherical shell of cometary nuclei that marks the outermost boundary of the Sun's gravitational influence. From these remote regions, the particles begin their long migration inward, carried by gravitational perturbations, solar radiation pressure, and the complex dynamics of orbital mechanics. The timescales involved in this cosmic migration make human history seem like a brief flicker. Computer models suggest that a particle originating in the outer solar system might require anywhere from hundreds of thousands to tens of millions of years to spiral inward to Earth's vicinity. During this immense journey, the grain experiences billions of thermal cycles as its elliptical orbit carries it alternately closer to and farther from the Sun. It encounters gravitational influences from all the major planets, each encounter subtly altering its trajectory in ways that accumulate over time into significant changes in orbital characteristics. Throughout this journey, the particle slowly loses mass. The process begins with the sublimation of volatile materials, water ice, frozen carbon dioxide, and other compounds that vaporize when exposed to solar radiation. Gradually, only the most refractory materials remain: silicates, metals, and carbon-rich compounds that can withstand the harsh environment of interplanetary space. By the time a particle reaches the inner solar system, it has been refined by the cosmic furnace into a concentrate of the most durable substances in the universe. The physics governing these microscopic wanderers reveals phenomena that operate on scales both smaller and larger than everyday experience. Individual particles respond to forces that would be negligible for larger objects, but become dominant at micrometer dimensions. The pressure exerted by sunlight, for instance, becomes a significant factor in determining orbital evolution when applied to surfaces with such high area-to-mass ratios. A dust grain experiences solar radiation pressure as a constant gentle push that gradually modifies its orbit over geological time. Electromagnetic forces also play crucial roles in the dynamics of interplanetary dust. Many particles acquire electric charges through interaction with the solar wind and cosmic radiation. These charged grains then respond to the Sun's magnetic field and the complex electromagnetic environment of interplanetary space. In some regions, particularly near planetary magnetospheres, electromagnetic forces can become more important than gravity in determining particle trajectories. The journey inward transforms each grain in subtle but measurable ways. Laboratory analysis of collected particles reveals evidence of space weathering processes that have no terrestrial analogue. Solar wind implantation creates microscopic layers of altered material on particle surfaces. Cosmic ray bombardment generates distinctive isotopic signatures that record the duration and intensity of radiation exposure. Even the act of spiraling inward leaves its mark, as particles that have spent more time in the inner solar system show greater degrees of thermal processing than those recently arrived from the outer regions. Some of the most remarkable particles are those that have survived multiple passages through the asteroid belt, where the density of debris creates a kind of cosmic sandblasting environment. These grains bear the accumulated damage of countless microscopic impacts, their surfaces sculpted into complex topographies that record the violence of interplanetary space. Yet they continue their journey, testament to the remarkable durability of matter organized at the smallest scales of cosmic architecture. The concept of drift takes on profound meaning when applied to these cosmic snowflakes. Unlike terrestrial precipitation, which falls in response to gravity over timescales measured in minutes or hours, interplanetary dust drifts through space over timescales that encompass the rise and fall of entire species on Earth. A particle that began its earthward journey when the first complex life appeared in Earth's oceans might only now be approaching the final stages of its cosmic migration. Current observations suggest that approximately 40,000 of these particles settle onto each square kilometre of Earth's surface every day. This estimate, derived from satellite measurements, atmospheric sampling, and analysis of terrestrial accumulation sites, carries with it uncertainties that reflect the fundamental challenge of measuring phenomena at such small scales across such vast distances. The actual flux likely varies with solar activity, planetary alignments, and the passage of Earth through different regions of the interplanetary debris field. The particles themselves display a remarkable diversity of composition and structure that reflects the heterogeneous nature of their origins. Some contain pristine materials that formed in the outer reaches of the solar nebula, preserving chemical and isotopic signatures from the earliest epochs of solar system history. Others show evidence of extensive thermal processing, their mineralogy altered by repeated exposure to solar radiation. A few contain organic compounds that formed through chemical processes in the cold vacuum of interstellar space. Molecular fossils from an era before the Sun existed. The study of these microscopic visitors requires techniques that push analytical chemistry to its absolute limits. Individual particles must be manipulated using focused ion beams and other nanoscale tools. Their chemical composition is determined using instruments capable of detecting individual atoms. Their crystal structure is revealed through electron diffraction patterns that require interpretation by specialists familiar with mineral phases that exist nowhere on Earth. Perhaps most remarkably, some of these particles contain presolar grains, microscopic diamonds, silicon carbide crystals, and other materials that condensed around stars that died before the Sun was born. These stellar fossils, embedded within the already microscopic dust grains like Russian nesting dolls made of cosmic matter, represent samples of the interstellar medium that existed billions of years ago. They carry within their crystal lattices the nuclear signatures of stellar nuclear synthesis, the element-building processes that occur in the cores of dying stars. The gentle drift of these cosmic snowflakes continues without pause, unaffected by human activity, climate change, or the passage of geological ages. Right now, particles that began their journey when the first animals crawled onto land are settling through Earth's upper atmosphere, their cosmic wandering finally approaching its end. Others, launched by comet outgassing events during the last ice age, still drift somewhere in the outer solar system, decades away from their eventual encounter with Earth's gravitational embrace. Only took a few million years for each grain to complete its migration from the outer darkness to Earth's welcoming atmosphere. And in that patient journey, each particle has become a messenger carrying news from regions of space that no human-made probe has ever visited. A microscopic time capsule preserving samples of cosmic processes that occurred long before observers evolved to wonder at their meaning. In the pristine expanses of Antarctica, where human footprints remain rare and the air carries no trace of industrial contamination, researchers have discovered one of the most extraordinary libraries ever assembled. This archive requires no shelves, no cataloguing system, no climate control beyond what nature provides. Instead, it exists as microscopic particles embedded within layers of ice that have accumulated over hundreds of thousands of years, each annual snowfall preserving a record of cosmic visitors that settled from space during Earth's slow journey around the Sun. The collection process began long before humans existed to recognize its significance. Each winter, as temperatures plunged and moisture crystallized from the thin Antarctic air, cosmic dust particles became incorporated into falling snow with the same gentle inevitability that captures pollen or volcanic ash. The particles settled onto the growing ice sheet, where they were buried by subsequent snowfalls and compressed into the glacial record, layer by layer, season by season. The ice preserved samples of interplanetary material spanning geological ages. Modern ice core drilling operations, originally designed to study ancient climates, have inadvertently created the most comprehensive collection of extraterrestrial material available for scientific study. When researchers extract cylindrical cores from the Antarctic ice sheet, they recover not only trapped atmospheric gases and volcanic debris, but also microscopic samples of cosmic dust that fell during every year represented in the ice column. A single metre of ice core may contain thousands of these particles, each one preserved with the pristine clarity that only polar conditions can provide. The preservation is so complete that individual particles retain their original surface textures, chemical compositions, and even delicate structural features that would be destroyed by terrestrial weathering processes under scanning electron microscopes. These cosmic visitors display the same intricate surface topographies they possessed when they first entered Earth's atmosphere. Some show the characteristic signs of gentle atmospheric entry heating, others reveal complex mineral assemblages that could only have formed in the exotic environments of interplanetary space. The Antarctic collection offers researchers something impossible to obtain through any other means, a time series record of cosmic dust flux spanning hundreds of millennia. By analysing particles from different depths within ice cores, scientists can reconstruct how the rate of cosmic dust accumulation has varied throughout Earth's recent geological history. They can identify periods when comet impacts increased the dust flux, correlate particle chemistry with known meteor shower events, and trace the gradual evolution of interplanetary debris fields over time scales far longer than human observation. Some of the most remarkable discoveries have emerged from the deepest ice cores, where particles preserved for hundreds of thousands of years reveal compositions and structures that differ subtly from contemporary cosmic dust. These ancient samples suggest that the interplanetary environment has undergone slow but measurable changes as the solar system has evolved. The size distribution of particles, their chemical compositions, and their isotopic signatures all show variations that may reflect changes in comet activity, asteroid collision rates, or even the passage of the solar system through different regions of interstellar space. The process of extracting and analysing these particles requires extraordinary patience and precision. Ice core sections must be melted in ultra-clean laboratory environments to prevent contamination from terrestrial dust. The resulting meltwater is filtered through systems capable of capturing particles just a few micrometers in diameter. Each filter is then examined grain by grain under high magnification microscopes, with promising candidates selected for detailed chemical and isotopic analysis. The isotopic signatures preserved in these particles provide windows into processes that occurred billions of years ago and trillions of kilometers away. Oxygen isotope ratios reveal the temperature and chemical conditions under which the particles first condensed from gas. Silicon and magnesium isotopes carry information about nuclear synthesis in the stellar cores where these elements were forged. Some particles contain isotopic anomalies so distinctive they can be traced to specific types of stellar environments. Red giant stars, supernovae, or the asymptotic giant branch stars where much of the galaxy's carbon was created. Perhaps most intriguingly, the Antarctic Archive preserves evidence of rare events that might otherwise go undetected. During years when large comets made close approaches to the Sun, the cosmic dust flux increased dramatically as these ancient visitors shed vast quantities of material. The ice cores record these events as spikes in extraterrestrial particle concentration, creating a record of comet activity that extends far beyond the brief span of human astronomical observation. The organic chemistry preserved in these particles tells stories of molecular evolution in environments utterly unlike anything found on Earth. Complex carbon compounds, formed through reactions in the cold vacuum of interstellar space, remain stable within the ice matrix for geological ages. These molecular fossils include polycyclic aromatic hydrocarbons, amino acid precursors, and other compounds that may have played crucial roles in the chemical evolution that eventually led to life on Earth. Some particles recovered from Antarctic ice show signs of having originated beyond the solar system entirely. These interstellar visitors, captured during the solar system's passage through dense regions of the interstellar medium, carry chemical and isotopic signatures that differ markedly from locally produced cosmic dust. Their presence in the ice record provides direct samples of the matter that fills the space between stars, material that forms the raw material from which future solar systems will eventually condense. The seasonal variations preserved in the ice reveal the subtle rhythms of cosmic dust accumulation throughout the year. During certain months, when Earth's orbital motion carries it through regions of higher debris density, particle concentrations in the ice increase measurably. These seasonal patterns, repeated year after year in the glacial record, provide confirmation of the organized structure within the interplanetary dust cloud and demonstrate how Earth's changing position relative to this debris field affects the rate of extraterrestrial material accumulation. Recent advances in analytical techniques have enabled researchers to perform increasingly sophisticated analyses on ever smaller samples. Individual particles weighing less than a picogram can now be analysed for their complete chemical composition, crystal structure, and isotopic signatures. These capabilities have revealed that even particles that appear similar under optical microscopy often display remarkable diversity in their detailed properties, reflecting the complex and varied processes that shaped them during their cosmic journeys. The mystery of seasonal variations in particle chemistry adds another layer of complexity to the Antarctic archive. Cosmic dust that arrives during different times of year shows subtle but measurable differences in composition and structure, suggesting that Earth encounters debris streams with distinct origins and evolutionary histories as it follows its orbital path around the Sun. These compositional variations provide clues about the three-dimensional structure of the interplanetary dust cloud and the processes that organize debris into streams and clusters. The Antarctic collection continues to grow with each passing season, as fresh snowfall incorporates contemporary cosmic dust into the ongoing glacial record. Current accumulation rates suggest that future researchers will eventually have access to ice core samples spanning millions of years, creating an unparalleled archive of solar system evolution preserved in crystalline clarity. The particles falling today will join their predecessors in the polar ice, adding new chapters to a story written in microscopic detail across the vast scales of cosmic time. In the pristine silence of the Antarctic interior, where the only sounds are the whisper of wind across ice and the distant crack of shifting glaciers, this cosmic library grows grain by grain, breath by breath, preserving samples of infinity and the patient accumulation of polar snow. Only took a few 100,000 years to build an archive of the universe written in ice and starlight, and the collection continues, adding its microscopic treasures to the frozen memory of a planet that has been gathering evidence of its cosmic neighbourhood since the ice began to fall. The Moon maintains its own silent archive of cosmic dust accumulation, a library written not in ice but in the airless vacuum that has preserved samples of interplanetary material for billions of years. Unlike Earth, where atmospheric weathering and geological processes continuously erase evidence of cosmic bombardment, the lunar surface offers a nearly perfect preservation environment where particles that settled during the earliest epochs of solar system history remain essentially unchanged, embedded in the regolith like fossils frozen in time. When the Apollo astronauts returned from their expeditions carrying sealed containers of lunar soil, they unknowingly brought back some of the most comprehensive samples of ancient cosmic dust ever collected. The grey powder that clung to their spacesuits and equipment contained not only pulverized lunar bedrock, but also countless microscopic particles that had drifted through interplanetary space for millions of years before settling onto the Moon's unprotected surface. Each handful of lunar regolith represents a mixture of local and extraterrestrial materials, a cosmic sediment that has been accumulating without interruption since the Moon's formation. The preservation conditions on the lunar surface approach the ideal for maintaining cosmic dust in its original state. With no atmosphere to create oxidizing conditions, no water to drive chemical reactions, and no biological activity to contaminate samples, particles that land on the Moon remain essentially unchanged for geological ages. Temperature variations between lunar day and night do subject the material to thermal cycling, but without the presence of moisture or reactive gases. These temperature swings cause minimal alteration to the particle's fundamental properties. Laboratory analysis of lunar soil samples has revealed that between 1 and 2% of the regolith consists of extraterrestrial material, cosmic dust particles that accumulated over the Moon's 4 billion year history. This percentage may seem small, but it represents an enormous quantity of interplanetary material when distributed across the Moon's entire surface. Scientists estimate that the upper layers of lunar regolith contain somewhere between 10 to the 11th and 10 to the 12th kilograms of cosmic dust, making the Moon's surface one of the largest accessible repositories of extraterrestrial matter in the inner solar system. The isotopic signatures preserved in these particles provide unprecedented insights into the evolution of the interplanetary dust environment over geological time. Unlike terrestrial samples, which represent only the most recent accumulation, lunar soil contains particles that settled billions of years ago, when the solar system was young and the interplanetary environment was dramatically different from its current state. Heavy bombardment periods, ancient comet impacts, and the gradual evolution of asteroid belt dynamics are all recorded in the microscopic debris embedded within lunar regolith. Some of the most remarkable discoveries has come from the analysis of individual particles extracted from Apollo soil samples. These microscopic grains, painstakingly separated from the lunar matrix using techniques that can isolate objects smaller than bacteria, display compositions and structures that reveal their extraterrestrial origins with unmistakable clarity. Many contain mineral assemblages that could not have formed under lunar conditions, isotopic ratios that differ markedly from solar system norms, and organic compounds that bear the chemical signatures of interstellar space. The lunar regolith acts as a kind of natural mass spectrometer, concentrating and preserving samples of cosmic dust that would be difficult or impossible to study through any other means. The absence of atmospheric entry heating means that even the most delicate particles arrive at the lunar surface in pristine condition, their original textures and chemical compositions intact. Volatile compounds that would be lost during passage through Earth's atmosphere remain preserved in lunar samples, providing insights into the chemistry of interplanetary space that cannot be obtained from terrestrial collections. Recent reanalysis of archived Apollo samples using modern analytical techniques has revealed details that were invisible to earlier generations of instruments. Secondary ion mass spectrometry, capable of detecting trace elements at concentrations measured in parts per billion, has identified exotic isotopic signatures that point to stellar environments where these particles originally formed. Transmission electron microscopy reveals crystal structures and mineral phases that provide clues about the physical conditions these grains experienced during their cosmic journeys. The distribution of cosmic dust within lunar soil samples provides information about accumulation rates and flux variations over geological time. By analysing samples from different Apollo landing sites and different depths within the regolith, researchers can reconstruct how the cosmic dust environment has evolved as the solar system has aged. The data suggest that accumulation rates have varied significantly throughout lunar history, with periods of enhanced bombardment corresponding to major disruptions in the asteroid belt and increased comet activity. Some particles in lunar soil display evidence of multiple cosmic ray exposure events, suggesting complex histories that involved ejection from their parent bodies, long periods of interplanetary travel, and eventual capture by the Earth-Moon system. These multiply exposed grains carry within their crystal lattices the accumulated damage from billions of years of cosmic radiation, creating microscopic records of radiation environments in different regions of the solar system and different epochs of solar system evolution. The lunar samples also preserve evidence of the early solar system's violent history in ways that terrestrial samples cannot. During the late heavy bombardment, approximately 4 billion years ago, when asteroids and comets pummeled the inner planets with unprecedented intensity, the Moon's surface was resurfaced by impact events that mixed deep crustal material with contemporary cosmic dust. The resulting breccias contain fragments of very ancient cosmic dust embedded within impact melt rocks, preserving samples of the interplanetary environment from the earliest phases of planetary evolution. Advanced analytical techniques have revealed that some particles in lunar regolith contain presolar grains, microscopic diamonds, silicon carbide crystals, and other materials that condensed around stars that existed before the Sun formed. These stellar fossils, embedded within cosmic dust particles that are themselves embedded within lunar soil, represent samples of the interstellar medium that existed billions of years ago. They carry isotopic signatures of nuclear synthesis processes that occurred in stellar cores that completed their evolution before the solar nebula began to collapse. The organic chemistry preserved in lunar cosmic dust particles tells stories of molecular evolution in environments completely isolated from biological processes. Complex carbon compounds formed through purely chemical reactions in the vacuum of space remain stable within lunar samples for geological ages. These molecular fossils include compounds that may have served as precursors to the chemistry that eventually led to life on Earth, preserved in lunar samples with clarity that cannot be achieved in terrestrial environments. The absence of atmospheric shielding means that the Moon continues to accumulate cosmic dust at rates that can be measured and studied in real time. Current estimates suggest that approximately 10 to the minus 15 grams of cosmic dust settle onto each square centimetre of lunar surface every year, a rate so low that it would take millions of years to accumulate a layer thick enough to be visible to the naked eye. Yet, significant enough to continuously add new samples to the lunar archive. Future lunar missions will likely focus on systematic sampling of regolith from different regions and depths, creating a comprehensive map of cosmic dust distribution across the Moon's surface and throughout its geological history. The lunar far side, permanently shielded from Earth's gravitational influence and magnetic field, may preserve cosmic dust samples with compositions and structures that differ from those found in near-side regolith. The polar regions, where permanently shadowed craters have collected material for billions of years, represent another frontier for cosmic dust research. The Moon's role as a natural collector and preserver of cosmic dust makes it an invaluable resource for understanding the history and evolution of the interplanetary environment. Unlike any terrestrial archive, the lunar regolith preserves samples spanning the entire history of the solar system, from the earliest epochs of planetary formation to the present day. Each grain of lunar soil contains within it microscopic samples of cosmic dust that tell stories of stellar evolution, interplanetary dynamics, and the slow chemical evolution of the space between worlds. In the vacuum silence of the lunar surface, where no wind disturbs the ancient dust, and no weather erases the records of cosmic bombardment, this microscopic archive continues to grow particle by particle, preserving evidence of the universe's ongoing evolution in a museum without walls or atmosphere. The grey powder that future astronauts will find beneath their boots represents billions of years of patient accumulation. Each microscopic grain a page in the longest book ever written, a story told in the language of atoms and starlight across the immeasurable distances between worlds. Only took 4 billion years to build a library made of vacuum and cosmic debris, and still the collection grows, adding its ancient treasures to the airless memory of a world that has been gathering evidence of cosmic history since the solar system learned to dream in stone and shadow. As comets swing through their ancient orbits, approaching the sun's warmth after decades or centuries in the frozen darkness beyond the planets, they begin a process of transformation that has been painting streams of particles across the solar system for billions of years. These icy wanderers, remnants from the solar system's formation, carry within their nuclei the accumulated debris of countless previous passages, layers of dust and rocky material embedded in matrices of frozen water, carbon dioxide, and more exotic ices that sublimate only under the most extreme conditions. The process begins subtly, when a comet still lies beyond the orbit of Jupiter and solar heating remains too weak to cause significant changes. At these distances, only the most volatile compounds begin to stir, creating the faintest wisps of atmosphere around the nucleus. But as the comet continues its inward journey, crossing the orbits of Mars and approaching Earth's distance from the Sun, the transformation accelerates dramatically. Solar radiation penetrates the surface layers, causing subsurface ices to sublimate and creating pressures that fracture the comet's crust and release jets of gas and embedded particles. Each jet carries with it microscopic debris that has been locked within the comet's interior since its formation in the outer reaches of the solar nebula. These particles, liberated after billions of years of frozen storage, begin their own independent journeys through interplanetary space. Some follow trajectories that will eventually carry them into the Sun's atmosphere, where they will be vaporized in temperatures that exceed those found in stellar cores. Others are flung outward by the pressure of solar radiation, beginning migrations that may last millions of years before they encounter a planetary atmosphere or gravitational field. The streams of particles left behind by comet passages create some of the most predictable phenomena in astronomy. Earth's orbital motion carries it through these debris trails with clockwork regularity, producing the annual meteor showers that have captivated human observers for millennia. The Perseids, Geminids, Leonids, and dozens of other named showers represent Earth's encounters with particles shed by specific comets during their historical approaches to the Sun. But for every dramatic meteor that creates a visible streak across the night sky, countless thousands of smaller particles make the same journey through Earth's atmosphere with such gentle velocity that they arrive at the surface essentially intact. These are the cosmic dust grains that interest researchers most, particles small enough to be slowed by atmospheric friction rather than vaporized by it, allowing them to settle onto the planet's surface carrying their original chemical and structural information. Computer simulations of comet outgassing reveal the complex dynamics that govern particle release and subsequent evolution. As subsurface ices sublimate, they create cavities and fissures that can suddenly rupture, releasing bursts of material into space. High-speed cameras aboard spacecraft that have visited comets directly have captured these events in real time, showing fountains of debris erupting from specific locations on the nucleus surface with velocities measured in hundreds of meters per second. The composition of particles within comet trails varies significantly depending on the depth from which they originated within the nucleus. Surface layers, repeatedly processed by previous solar approaches, yield particles that have been altered by thermal cycling and radiation exposure. Deeper materials, freshly exposed by outgassing events, preserve chemical and isotopic signatures from the earliest epochs of solar system formation. Some particles contain organic compounds that formed in the interstellar medium before the Sun existed, molecular fossils that survived incorporation into the comet and billions of years of storage in the outer solar system. The orbital mechanics of particle dispersal create trails that can persist for centuries or millennia after the parent comet has completed its passage. Solar radiation pressure and gravitational perturbations from the planets gradually spread these particles along the comet's orbital path, creating ribbons of debris that can extend across significant fractions of the solar system. Mathematical models suggest that some comet trails contain particles with dispersal ages spanning hundreds of thousands of years, representing material shed during numerous historical passages. Recent space missions have provided unprecedented insights into the real-time process of comet outgassing and particle release. The European Space Agency's Rosetta mission, which spent 2 years in close proximity to Comet 67P/Churyumov-Gerasimenko, documented the day-to-day evolution of outgassing activity as the comet approached and then receded from the Sun. Its instruments detected particles being released at rates that varied dramatically with solar heating, surface topography, and the composition of subsurface materials. The particle release process exhibits remarkable complexity, with different regions of the comet nucleus showing distinct patterns of activity. Some areas produce steady streams of fine dust, while others generate sporadic bursts of larger fragments. The orientation of the comet's rotation axis relative to the Sun determines which regions receive the most heating during different phases of the orbit, creating seasonal variations in particle production that can persist for months as the comet continues its journey. Spectroscopic analysis of fresh comet trails reveals the presence of crystalline water ice, organic compounds, and silicate minerals in proportions that vary from comet to comet and even within different regions of the same nucleus. These compositional differences reflect the heterogeneous nature of the solar nebula from which comets formed, preserving evidence of chemical gradients and thermal processing that occurred during the earliest phases of planetary system evolution. The study of comet trails has revealed unexpected connections between these ancient visitors and other phenomena in the solar system. Some streams of particles appear to be gravitationally focused by Jupiter's influence, creating enhanced densities in specific regions of interplanetary space. Others show evidence of collisional evolution, where particles within the trail have collided and fragmented over geological time, creating complex size distributions that reflect millions of years of mutual bombardment. Laboratory analysis of particles collected from known comet trails provides direct samples of materials that formed in the coldest and most distant regions of the solar system. These particles often contain isotopic anomalies that indicate formation temperatures approaching absolute zero, chemical compositions that include rare noble gas isotopes, and organic molecules that could only have formed through reactions occurring over millions of years in the vacuum of space. The temporal evolution of comet trails creates archaeological opportunities for studying solar system history. Older particles within a trail carry evidence of the interplanetary environment as it existed decades or centuries ago, while fresh material reflects contemporary conditions. This temporal stratification allows researchers to reconstruct changes in solar activity, planetary positions, and cosmic dust flux over timescales that bridge the gap between direct observation and geological records. Some of the most remarkable discoveries have emerged from the analysis of particles that originated from comets with extremely long orbital periods, visitors that return to the inner solar system only once every few thousand years. These ancient wanderers carry within their nuclei materials that have remained essentially unaltered since the solar system's formation, preserved in the deep freeze of the outer Oort cloud where temperatures remain constant at just a few degrees above absolute zero. The continuing process of comet outgassing ensures that the interplanetary dust environment remains dynamic, constantly refreshed by new material from the solar system's most distant regions. Current estimates suggest that comets contribute between 10 and 100 tons of fresh dust to the inner solar system each day, a flux that varies significantly with the orbital phases of active comets and the occurrence of new arrivals from the Oort cloud. Tonight, as Earth continues its orbital journey through space, the planet passes through invisible streams of particles shed by comets that approached the Sun decades or centuries ago. These microscopic travellers, finally completing journeys that began in the frozen darkness beyond Neptune, settle gently onto the planet's surface carrying samples of ice and starlight from the most distant reaches of the Sun's gravitational domain. Only took a few million years for each trail to disperse across the inner solar system, and still the ancient streamers continue their patient drift, painting highways of cosmic dust along the pathways travelled by wandering ice mountains in their eternal dance around our star. In the vast ring of debris that orbits between Mars and Jupiter, a grinding mill has been operating continuously for over 4 billion years, slowly but inexorably pulverizing solid rock into microscopic fragments that eventually find their way throughout the inner solar system. This asteroid belt, containing hundreds of thousands of rocky bodies ranging from dwarf planets hundreds of kilometers across to boulders no larger than houses, represents the remnant of a planetary formation process that never quite succeeded in assembling its scattered materials into a single coherent world. The grinding process operates through the fundamental physics of orbital mechanics and collision dynamics, driven by gravitational resonances with Jupiter that ensures certain orbital zones remain perpetually unstable. Bodies that venture into these resonance regions experience repeated gravitational perturbations that gradually increase their orbital eccentricity, eventually leading to crossing orbits and inevitable collisions. When two asteroids meet at relative velocities measured in kilometers per second, the kinetic energy released in the impact can shatter both bodies completely, creating clouds of fragments that begin their own complex orbital evolution. Each collision event generates a cascade of debris spanning an enormous range of sizes, from large fragments that may themselves become asteroids to microscopic dust grains that are immediately subject to non-gravitational forces. The largest pieces retain enough mass to follow predictable orbital paths determined primarily by gravitational influences. Intermediate-sized fragments experience complex dynamics involving both gravity and radiation pressure. The smallest particles, those in the size range that concerns cosmic dust researchers, find their orbital evolution dominated by the subtle but persistent effects of solar radiation. Computer simulations of asteroid belt evolution reveal that the current population of small bodies represents only a tiny fraction of the material that originally occupied this region of the solar system. Over billions of years, the grinding mill has reduced an initial mass equivalent to several Earth-sized planets into the current sparse collection of asteroids and the vast but nearly invisible population of microscopic debris that fills the space between them. The missing mass has been redistributed throughout the solar system, with some material spiraling into the Sun and other fragments scattered to the outer planets or beyond. The size distribution of particles created by asteroid collisions follows predictable mathematical relationships that reflect the physics of catastrophic fragmentation. Large impacts preferentially create many small fragments and few large ones, leading to power law distributions where the number of particles increases dramatically as size decreases. This means that for every meter-sized chunk of asteroid debris, there exist millions of particles in the cosmic dust size range, creating an enormous population of microscopic travellers that vastly outnumber their larger siblings. Recent space missions have provided direct observations of the asteroid belt environment, revealing the complexity of the collision process and the resulting debris clouds. The Dawn mission, which orbited both Vesta and Ceres, documented evidence of impact events ranging from ancient basin-forming collisions to recent cratering events that have scattered fresh debris into interplanetary space. These observations confirm that the grinding process continues at measurable rates, with new dust being generated continuously as asteroids continue their 4 billion-year dance of mutual destruction. The mineral composition of asteroid-derived cosmic dust reflects the diverse chemistry of the asteroid belt itself, where different regions contain bodies with dramatically different compositions and formation histories. Particles originating from S-type asteroids carry signatures of high-temperature processing that occurred in the inner regions of the solar nebula, while those from C-type asteroids preserve evidence of formation in cooler, more distant environments where volatile compounds could condense alongside rocky materials. Laboratory analysis of cosmic dust particles with confirmed asteroid origins reveals microscopic structures that record the violent conditions of their liberation from parent bodies. Many particles show evidence of shock metamorphism, displaying crystal structures that could only have formed under the extreme pressures generated during hypervelocity impacts. Others contain multiple mineral phases that indicate rapid cooling from temperatures exceeding 1000 degrees Celsius, conditions that exist only briefly during the most energetic collision events. The temporal evolution of debris clouds created by asteroid collisions demonstrates the complex interplay between gravitational and non-gravitational forces in determining particle trajectories. Immediately after a collision, fragments remain concentrated near the impact site, but over timescales measured in thousands to millions of years. Differential orbital evolution spreads the debris along the entire orbital path of the parent body. This dispersal process creates streams of particles that can persist long after the original collision event, contributing to the general background of cosmic dust throughout the inner solar system. Gravitational resonances with Jupiter not only trigger asteroid collisions, but also play crucial roles in determining the fate of the resulting debris. Particles that enter specific resonance zones experience orbital evolution that can eject them from the asteroid belt entirely, sending them on trajectories that may eventually intersect Earth's orbit. Other resonances create trapping regions where particles can remain confined for millions of years, slowly grinding against each other in a process that gradually reduces their average size through mutual collisions. The study of asteroid families, groups of asteroids that share similar orbital characteristics and compositions, provides insights into specific collision events that occurred millions of years ago. These families represent the large fragments from catastrophic disruption events, while the associated dust represents the microscopic debris from the same collisions. By analysing the properties of both large and small fragments, researchers can reconstruct the physics of ancient impact events and trace the subsequent evolution of the resulting debris clouds. Some of the most interesting particles in cosmic dust collections originate from asteroids that have undergone multiple generations of collision processing. These multiply fragmented grains carry within their structure evidence of several distinct impact events, creating complex archaeological records of the violence that characterizes asteroid belt dynamics. The isotopic signatures in such particles often show evidence of cosmic ray exposure spanning millions of years, indicating extended periods of small particle existence in interplanetary space. The asteroid belt's grinding mill operates with such efficiency that the average lifetime of a small body in certain regions can be measured in millions rather than billions of years. This means that much of the cosmic dust currently settling on Earth originated from asteroid collisions that occurred during relatively recent geological epochs, carrying samples of asteroid mineralogy that reflect conditions in the asteroid belt as they existed when complex life was already established on Earth. Advanced numerical models of asteroid belt evolution suggest that the grinding process exhibits episodic behavior, with periods of enhanced collision activity followed by intervals of relative quiescence. These variations may reflect the migration of large asteroids into new orbital configurations, the gravitational influence of planetary orbital evolution, or the arrival of new material from the outer solar system. The resulting variations in cosmic dust production create fluctuations in the flux of extraterrestrial material reaching Earth over geological time. Recent discoveries of asteroids with compositions unlike any known meteorites suggests that the cosmic dust collection process may provide access to materials from asteroid types that rarely survive atmospheric entry as large meteorites. These exotic compositions, preserved only in microscopic particles that can survive gentle atmospheric deceleration, offer insights into asteroid diversity that cannot be obtained through any other sampling method. The continuing operation of the asteroid belt's grinding mill ensures that the supply of cosmic dust remains constantly renewed, with fresh material being liberated from asteroid surfaces and interiors where it has remained unaltered since the solar system's formation. Current estimates suggest that asteroid collisions contribute tens of tons of microscopic debris to the cosmic dust environment each day, a production rate that has probably remained roughly constant for billions of years. In the cold darkness between Mars and Jupiter, where sunlight arrives with only a fraction of its terrestrial intensity, the ancient grinding mill continues its patient work, reducing mountains of stone to microscopic fragments that will eventually carry samples of the asteroid belt to every corner of the inner solar system. Only took 4 billion years to pulverize several planets' worth of rock into cosmic dust, and still the grinding continues, powered by the orbital mechanics of a planetary formation process that never quite managed to finish assembling its scattered building materials into a single world. In the vast emptiness between planets, where matter exists at densities approaching the absolute limits of measurement, a phenomenon operates with such subtlety that its effects become apparent only over time scales measured in millions of years. The Poynting-Robertson effect, named after the physicists who first described its theoretical basis in the early 20th century, acts as a cosmic broom that slowly but inexorably sweeps microscopic particles inward toward the Sun, transforming stable orbital motion into a gradual spiral that must inevitably end in solar immolation. The physics underlying this process emerge from the fundamental relationship between electromagnetic radiation and matter, operating at scales where the distinction between waves and particles begins to blur into quantum mechanical uncertainty. Sunlight carries momentum, a fact that becomes negligible for large objects but assumes paramount importance when applied to particles with dimensions measured in micrometers. When photons strike a cosmic dust grain, they transfer their momentum to the particle, creating forces that accumulate over time into measurable changes in orbital characteristics. The effect manifests through a subtle asymmetry in the way particles absorb and re-radiate solar energy. A dust grain orbiting the Sun absorbs photons primarily from the direction of its orbital motion, since its movement through space creates an apparent headwind of electromagnetic radiation. When the particle re-radiates this energy as thermal infrared radiation, however, the emission occurs isotropically in all directions from the grain's reference frame. This asymmetry creates a net force that opposes the particle's orbital motion, gradually reducing its orbital energy and causing it to spiral inward. The timescales involved in this cosmic deceleration process depend critically on particle size, with smaller grains experiencing more rapid orbital decay than larger ones. A particle 1 micrometer in diameter, typical of interplanetary dust, might require several million years to spiral from Earth's orbital distance to the Sun's surface. Larger particles, with lower surface area to mass ratios, can maintain stable orbits for tens or hundreds of millions of years. The smallest grains, approaching the wavelength of visible light, experience such strong radiation pressure that they may be blown out of the solar system entirely rather than spiraling inward. Computer simulations of particle orbital evolution reveal the remarkable complexity that emerges from this apparently simple physical process. As particles spiral inward, they pass through gravitational resonances with the planets that can temporarily capture them in quasi-stable configurations or eject them onto highly eccentric trajectories. The combined effects of radiation pressure, gravitational perturbations, and electromagnetic forces create a dynamic environment where individual particle trajectories become essentially unpredictable despite following deterministic physical laws. The Poynting-Robertson effect creates a natural sorting mechanism that segregates particles by size and composition throughout the solar system. Materials with different optical properties experience different rates of orbital decay, leading to gradual chemical fractionation as the cosmic dust population evolves. Particles rich in iron and other metals, which absorb solar radiation efficiently, spiral inward more rapidly than those composed primarily of silicates or organic compounds. This selective removal process gradually alters the composition of the interplanetary dust environment over geological time. Laboratory studies of collected cosmic dust particles reveal evidence of the sorting process in action. Particles recovered from different collection sites show systematic variations in composition that correlate with their inferred orbital histories. Those that have spent longer periods in the inner solar system display evidence of thermal processing and compositional evolution that reflects millions of years of exposure to intense solar radiation during their gradual inward migration. The discovery of this orbital decay mechanism resolved a long-standing puzzle in planetary science: how the solar system maintains its observed population of cosmic dust despite the obvious absence of any mechanism to create stable long-term orbits for microscopic particles. The answer lies in the balance between dust production through asteroid collisions and comet outgassing, and dust removal through Poynting-Robertson drag and other non-gravitational effects. The current dust population represents a dynamic equilibrium between these competing processes. Recent spacecraft missions have provided direct measurements of the Poynting-Robertson effect in operation, detecting subtle changes in particle trajectories that confirm theoretical predictions about radiation-driven orbital evolution. The Ulysses mission, during its journey through the outer solar system, documented systematic variations in cosmic dust flux that reflect the preferential removal of certain particle sizes from specific orbital zones. These observations provide quantitative confirmation of models that predict how radiation pressure shapes the distribution of microscopic matter throughout interplanetary space. The effect operates with particular efficiency in the inner solar system, where solar flux reaches intensities sufficient to drive rapid orbital evolution for particles smaller than about 100 micrometers. This creates a natural boundary beyond which particles of different sizes follow dramatically different evolutionary paths. Large meteoroids, essentially immune to radiation pressure, can maintain stable orbits for billions of years. Microscopic dust, subject to strong Poynting-Robertson drag, must either spiral into the Sun or escape the solar system entirely within relatively short geological periods. The mathematical description of particle orbital evolution under radiation pressure reveals elegant connections between electromagnetic theory, celestial mechanics, and thermodynamics. The equations governing this process are nonlinear and coupled, meaning that small changes in initial conditions can lead to dramatically different evolutionary outcomes. This sensitivity to initial conditions creates a kind of dynamical chaos, where individual particle trajectories become unpredictable while statistical populations follow well-defined evolutionary trends. Advanced computer models incorporating the Poynting-Robertson effect have revolutionized understanding of cosmic dust distribution throughout the solar system. These simulations reveal that the current dust population exists in a state of continuous renewal, with fresh material from asteroids and comets replacing particles that have been removed by radiation pressure and other processes. The models predict that without continuous replenishment, the interplanetary dust environment would be swept clean of microscopic particles within about 10 million years. The effect also influences the evolution of larger debris, including meteoroids and small asteroids that exist at the boundary between gravitational and radiation-dominated dynamics. For objects in this intermediate size range, radiation pressure can significantly perturb their orbits over geological time. potentially explaining some of the observed complexity in meteor shower patterns and the orbital distribution of near-Earth asteroids. Recent theoretical work has identified additional subtleties in the radiation pressure mechanism that operate under specific conditions found in interplanetary space. The Yarkovsky effect, caused by thermal re-radiation from rotating objects, can either accelerate or decelerate orbital motion depending on the direction of rotation. Electromagnetic forces, generated by the interaction between charged particles and the solar magnetic field, create additional perturbations that modify the simple predictions of classical Poynting-Robertson theory. The discovery that cosmic dust particles often acquire electric charges through interaction with the solar wind and cosmic radiation has revealed another layer of complexity in their orbital evolution. Charged particles respond to electromagnetic fields in ways that can either enhance or counteract radiation pressure effects, creating population dynamics that depend on the detailed electromagnetic environment of interplanetary space, as well as the optical properties of the particles themselves. Current research focuses on understanding how the Poynting-Robertson effect operated during different epochs of solar system history. When solar luminosity, planetary configurations, and cosmic dust production rates differed from their present values, these studies suggest that the efficiency of dust removal has varied significantly over geological time, potentially explaining observed variations in cosmic dust flux recorded in terrestrial sediments and lunar samples. In the silent vacuum of interplanetary space, where individual particles drift through emptiness for millions of years before encountering another grain of matter, the cosmic broom continues its patient work, sweeping microscopic debris inward toward the solar furnace with forces so gentle they barely register on the most sensitive instruments, yet inexorable enough to determine the fate of every dust grain in the solar system. Only took radiation pressure 4 billion years to establish a cosmic cleaning system that operates continuously without maintenance, and still the ancient broom sweeps inward, powered by starlight itself, ensuring that the space between worlds remains dynamically young despite the passage of geological ages. When cosmic dust particles finally encounter Earth's atmosphere after their long journey through interplanetary space, they experience a form of atmospheric entry so gentle that it challenges the conventional understanding of what happens when extraterrestrial objects meet our planet's protective gaseous envelope. Unlike the dramatic meteors that streak across the night sky in brilliant displays of atmospheric friction, these microscopic travelers approach Earth with velocities so modest and sizes so small that they settle through the atmosphere with the same gentle inevitability as terrestrial dust motes drifting in a sunbeam. The process begins at altitudes exceeding 100 kilometers, where the atmosphere exists as little more than a whisper of gas molecules scattered through what remains essentially a vacuum. At these heights, cosmic dust particles encounter their first atmospheric molecules with such infrequency that individual collisions become discrete events separated by significant distances and time intervals. The particles, travelling at velocities typically ranging from 11 to 70 kilometers per second relative to Earth's surface, gradually begin to transfer their kinetic energy to the rarefied atmospheric gases. The physics of this interaction operates in a regime completely different from that experienced by larger meteoroids, where atmospheric compression creates shock waves and temperatures exceeding those found in stellar cores. For particles smaller than about 100 micrometers, the mean free path between molecular collisions approaches or exceeds the particle's own dimensions, creating conditions where conventional fluid dynamics breaks down and must be replaced by kinetic theory describing individual molecular interactions. As the particles descend through the increasingly dense atmospheric layers, they undergo a process of gradual deceleration that can extend over dozens of kilometers of altitude and tens of minutes of time. The drag forces acting on these microscopic objects scale with their cross-sectional area, while their inertia depends on their mass and thus their volume. This fundamental geometric relationship means that smaller particles experience proportionally greater deceleration, causing them to shed their cosmic velocities much more efficiently than larger objects. Temperature measurements of cosmic dust particles during atmospheric entry reveal that most never exceed a few hundred degrees Celsius, temperatures insufficient to cause significant melting or chemical alteration of their constituent minerals. This gentle heating allows the particles to preserve their original crystal structures, chemical compositions, and even delicate surface features that would be obliterated during the violent atmospheric entry experienced by larger meteoroids. Some particles show evidence of minimal surface heating that created thin glassy coatings, but the underlying grain structure remains essentially unaltered. The deceleration process exhibits remarkable efficiency in converting cosmic velocities to terrestrial ones. Computer simulations of particle atmospheric entry show that typical cosmic dust grains lose more than 99% of their initial kinetic energy during passage through the upper atmosphere, emerging into the lower atmospheric layers with terminal velocities measured in centimeters per second rather than kilometers per second. This dramatic velocity reduction occurs without the explosive energy release that characterizes larger meteoroid entries. High-altitude aircraft equipped with specialized collection systems have captured cosmic dust particles during their descent through the stratosphere, providing direct samples of material that has recently completed atmospheric entry but has not yet been contaminated by terrestrial surface processes. These collections reveal particles with pristine extraterrestrial compositions and structures that confirm the gentle nature of their atmospheric passage. Scanning electron microscopy of freshly collected particles shows surface textures that could not have survived more energetic atmospheric interactions. The atmospheric entry process sorts particles by size and density through a complex interplay of aerodynamic forces and gravitational settling. Smaller particles, with their higher surface area to mass ratios, decelerate more completely and settle more slowly through the lower atmosphere. Larger particles retain more of their initial velocity and settle more rapidly. This natural fractionation process creates systematic variations in particle size distribution, with altitude that can be used to infer the characteristics of the original cosmic dust population. Recent atmospheric modeling studies have revealed unexpected complexity in the entry process, particularly regarding the role of particle rotation and shape in determining deceleration efficiency. Non-spherical particles, which constitute the majority of cosmic dust grains, can experience tumbling motion that affects their aerodynamic properties and heat distribution. Some particles appear to undergo partial fragmentation during atmospheric entry, breaking along planes of weakness created by cosmic ray damage or thermal cycling during their interplanetary journey. The chemical composition of cosmic dust particles influences their atmospheric entry behavior in subtle but measurable ways. Particles rich in volatile compounds may experience some mass loss through sublimation during the heating phase of atmospheric passage. Those containing metallic components may undergo limited oxidation as they encounter increasing concentrations of atmospheric oxygen at lower altitudes. However, these chemical modifications typically affect only the outermost surface layers, leaving the bulk composition essentially unchanged. Seasonal and latitudinal variations in atmospheric density create subtle differences in particle entry conditions that may affect the efficiency of cosmic dust collection at different times and locations. The atmosphere's response to solar heating creates vertical circulation patterns that can influence particle settling rates and horizontal distribution. During periods of high solar activity, increased atmospheric heating may extend the region of significant atmospheric drag to higher altitudes, potentially affecting the entry characteristics of the smallest particles. The electromagnetic properties of cosmic dust particles can also influence their atmospheric entry experience. Many particles acquire electric charges during their interplanetary journey through interaction with the solar wind and cosmic radiation. These charged particles may experience additional forces due to Earth's magnetic field and atmospheric electric fields, creating perturbations to their trajectories that can affect their geographical distribution and settling patterns. Laboratory simulations of cosmic dust, atmospheric entry, conducted using particle accelerators and specialized atmospheric chambers, have confirmed many theoretical predictions about the entry process while revealing additional complexities that emerge under realistic atmospheric conditions. These experiments demonstrate that the gentle entry mechanism operates reliably for particles across the size range that dominates cosmic dust collections, providing confidence in interpretations of collected particle properties as reflecting their original interplanetary characteristics. The study of cosmic dust atmospheric entry has implications beyond planetary science, offering insights into atmospheric physics at altitude regimes and density scales that are difficult to study through conventional means. The behavior of microscopic particles in rarefied gas environments provides data relevant to understanding atmospheric escape processes, aerosol dynamics in the upper atmosphere, and the interaction between interplanetary matter and planetary atmospheres throughout the solar system. Current research focuses on understanding how atmospheric entry efficiency has changed throughout Earth's history as atmospheric composition and density have evolved. During the Archean Eon, when Earth's atmosphere contained little oxygen and significantly less nitrogen, cosmic dust entry dynamics may have differed substantially from contemporary conditions. These historical variations in entry efficiency could have influenced the rate of extraterrestrial material delivery to Earth's surface during critical periods of early biological evolution. Advanced radar systems designed to detect atmospheric meteors have begun to identify the signatures of cosmic dust entry events, revealing that the atmosphere processes these microscopic visitors continuously rather than sporadically. The radar data suggests that cosmic dust entry occurs at rates consistent with spacecraft-based measurements of interplanetary dust density, providing independent confirmation of global cosmic dust flux estimates derived from other observation methods. In the thin air of the upper atmosphere, where space gradually yields to sky and cosmic travellers complete their million-year journeys with the gentleness of falling snow, the ancient rain continues its patient descent toward Earth's welcoming surface. Each particle carries within its structure the memory of interplanetary wandering and the promise of terrestrial rest. Settling through layers of increasingly dense air with the quiet inevitability of microscopic snowflakes drifting toward a planet that has been gathering cosmic dust since the atmosphere first learned to breathe, only took atmospheric physics a few billion years to perfect a delivery system capable of preserving cosmic treasures intact during their final descent. And still the gentle entry continues, bringing samples of infinity to a world patient enough to catch them as they fall, in the deepest reaches of Earth's oceans, where sunlight has never penetrated and water pressure exceeds that found anywhere else on the planet's surface. A different kind of sedimentation process has been quietly accumulating evidence of cosmic history for billions of years. The ocean floors serve as vast collection plates, gathering not only the terrestrial debris that washes down from continents and the biological remains of marine organisms, but also the microscopic cosmic visitors that settle through the entire water column before coming to rest in the abyssal sediments that carpet the ocean basins. The process begins when cosmic dust particles, having completed their gentle passage through Earth's atmosphere, encounter the ocean surface and begin their descent through kilometers of seawater toward the seafloor. Unlike terrestrial sediments, which can be transported horizontally for vast distances by ocean currents, cosmic dust particles settle primarily under the influence of gravity, creating a relatively undiluted record of extraterrestrial material accumulation that spans geological epochs. The deep ocean environment provides ideal preservation conditions, where cold temperatures, high pressure, and chemical isolation protect these cosmic visitors from the weathering processes that would rapidly destroy them in terrestrial environments. Laboratory analysis of deep-sea sediment cores retrieved from abyssal plains has revealed that cosmic dust comprises a measurable fraction of the total sediment accumulation in regions far from continental margins, in the most remote parts of the ocean basins, where terrestrial sediment flux remains minimal. Cosmic dust can constitute several % of the total sediment mass. This proportion varies systematically with distance from continents, ocean depth, and the local productivity of marine ecosystems, creating patterns that allow researchers to isolate the cosmic component from terrestrial and biological contributions. The sedimentation process operates with remarkable constancy over geological time, creating layer-by-layer records of cosmic dust accumulation that can be traced back millions of years into Earth's history. Sediment cores from the Pacific Ocean, where some regions accumulate material at rates of only a few millimeters per 1,000 years, preserve cosmic dust records with temporal resolution sufficient to detect variations in extraterrestrial material flux over timescales ranging from centuries to millions of years. These records provide unique insights into how the cosmic dust environment has evolved as the solar system has aged and planetary configurations have shifted. The chemical composition of cosmic dust preserved in marine sediments reveals signatures that distinguish extraterrestrial material from terrestrial sources with remarkable clarity. Platinum group elements, particularly iridium and osmium, occur in cosmic dust at concentrations far exceeding those found in Earth's crust, creating geochemical fingerprints that allow researchers to identify and quantify cosmic contributions to oceanic sedimentation. Isotopic ratios of these elements provide additional constraints, since cosmic dust often displays isotopic signatures that reflect nuclear synthesis processes in stellar environments. Advanced analytical techniques applied to marine sediment cores have revealed temporal variations in cosmic dust flux that correlate with astronomical events and solar system dynamics. Periods of enhanced cosmic dust accumulation appear to coincide with documented comet shower events, times when gravitational perturbations in the outer solar system increased the rate of comet delivery to the inner planets. Other flux variations may reflect the solar system's passage through dense regions of the local interstellar medium, where enhanced capture of interstellar dust temporarily increased the cosmic debris population. The size distribution of cosmic dust particles in marine sediments provides information about atmospheric entry processes and particle survival rates that cannot be obtained through any other sampling method. The ocean floor environment preserves particles across the entire size spectrum of cosmic dust, from submicron grains that barely register on analytical instruments, to larger particles approaching the threshold where atmospheric heating begins to cause significant alteration. This comprehensive size sampling reveals details about particle production mechanisms in interplanetary space, and their subsequent modification during atmospheric entry. Recent discoveries in marine sediment cores have identified layers with exceptionally high cosmic dust concentrations that may record specific astronomical events in Earth's history. Some of these enrichment events correlate with known impact crater ages, suggesting that large asteroid or comet impacts may have temporarily increased cosmic dust flux through the ejection of impact debris that eventually settled back to Earth's surface. Other enrichment events lack corresponding impact evidence, potentially indicating encounters with dense comet debris streams or passage through interstellar dust clouds. The preservation of organic compounds within cosmic dust particles buried in marine sediments has opened new avenues for studying the chemistry of interplanetary space over geological time. Cold, anoxic conditions on the deep ocean floor can preserve complex organic molecules for millions of years, including amino acids, polycyclic aromatic hydrocarbons, and other compounds that form through chemical processes in the vacuum of space. These molecular fossils provide direct evidence for the delivery of prebiotic organic matter to early Earth through cosmic dust accumulation. Microscopic examination of cosmic dust particles extracted from marine sediments reveals surface textures and internal structures that record their passage through different environments during their cosmic journey. Some particles display evidence of space weathering processes that operated during millions of years of interplanetary travel. Others show signs of partial atmospheric heating during entry, while still preserving their essential extraterrestrial characteristics. The diversity of preservation states provides insights into the range of conditions that cosmic dust experiences during its transition from interplanetary space to terrestrial environments. The isotopic composition of helium, neon, and other noble gases trapped within cosmic dust particles in marine sediments carries information about cosmic ray exposure ages and solar wind implantation that occurred during interplanetary transport. These isotopic signatures allow researchers to reconstruct the orbital histories of individual particles, estimating how long they drifted through space before encountering Earth and which regions of the solar system they may have visited during their cosmic wandering. Magnetostratigraphic analysis of sediment cores containing cosmic dust provides independent age constraints that allow precise dating of cosmic dust flux variations over the past several million years. By correlating cosmic dust abundance with magnetic polarity reversals recorded in the sediment magnetic minerals, researchers can construct detailed timelines of extraterrestrial material delivery that can be compared with astronomical records and theoretical models of solar system evolution. The study of cosmic dust in marine sediments has revealed unexpected connections between extraterrestrial material delivery and Earth's climate history. Some researchers have proposed that variations in cosmic dust flux may have influenced cloud formation processes in Earth's atmosphere, potentially affecting global climate patterns over geological time. While these connections remain speculative, the high-resolution records preserved in marine sediments provide the data necessary to test such hypotheses quantitatively. Current research focuses on extending cosmic dust records deeper into Earth's history by analyzing older marine sediments and correlating cosmic dust abundance with major geological and biological events. Preliminary studies of Mesozoic and Paleozoic sediment cores suggest that cosmic dust flux has varied significantly throughout Earth's history, with some periods showing accumulation rates several times higher than contemporary values. These variations may reflect changes in solar system dynamics, including the migration of giant planets and the evolution of asteroid belt structure over geological time. The global distribution of cosmic dust in marine sediments provides insights into atmospheric transport processes that operate after particles complete their initial descent through the water column. While most cosmic dust settles relatively close to where it first encounters the ocean surface, atmospheric circulation patterns can transport the finest particles over considerable distances before they finally settle into marine environments. These transport effects create subtle geographic variations in cosmic dust composition that reflect the mixing of material from different sources and atmospheric processing pathways. Recent advances in analytical geochemistry have enabled researchers to identify cosmic dust signals in marine sediments that are billions of years old, extending the record of extraterrestrial material delivery back to Earth's earliest geological epochs. These ancient cosmic dust signatures provide constraints on solar system conditions during the Archean and Proterozoic eons, when planetary configurations and cosmic dust production rates may have differed dramatically from their current values. The data suggests that Earth has been accumulating cosmic material continuously since the earliest formation of stable oceanic basins. The interaction between cosmic dust and marine biological processes creates additional complexity in sediment records. As microorganisms may selectively incorporate or exclude certain types of extraterrestrial particles during biomineralization processes, some marine organisms appear to concentrate cosmic dust particles in their skeletal structures, creating biological archives of cosmic material that can be traced through the fossil record. These biological processing effects must be considered when interpreting cosmic dust abundance data from sediment cores. Advanced computer models of oceanic sedimentation processes have revealed that cosmic dust distribution in marine sediments reflects a complex interplay between particle settling dynamics, ocean circulation patterns, and seafloor topography. Ridge systems and abyssal hills can create local variations in cosmic dust accumulation that complicate regional correlation studies. Understanding these physical processes is essential for accurately interpreting the cosmic dust record preserved in marine sediments and extracting reliable information about historical variations in extraterrestrial material flux. The discovery of cosmic dust particles with unusual isotopic signatures in ancient marine sediments has provided evidence for rare astronomical events that may have temporarily altered the cosmic dust environment. Some particles display isotopic anomalies consistent with formation in supernova explosions or other stellar environments, suggesting that Earth occasionally receives material from stellar sources beyond the local solar system. These exotic particles represent some of the rarest and most valuable samples of cosmic material available for laboratory study. In the eternal darkness of the ocean depths, where pressure creates silence and cold preserves memory, the seafloor continues its patient accumulation of cosmic treasures mixed with terrestrial sediments and biological remains. Each grain of cosmic dust that settles into the abyssal ooze adds another page to the longest geological record on Earth. A story written in microscopic particles that have travelled from the birth regions of planets to rest finally in the deepest archives of our world. Only took billions of years of oceanic sedimentation to build a library of cosmic history preserved in mud and starlight. And still the collection grows, layer by infinitesimal layer. In the quiet depths where time moves with the slowness of geological ages and space dust settles like snow that falls upward from the stars. Within each microscopic cosmic dust grain lies a chemical fingerprint more distinctive and revealing than any terrestrial signature. A molecular passport that records not only the particle's place of origin, but also the sequence of environments it encountered during its cosmic journey. These isotopic ratios, measured with instruments capable of detecting differences in atomic composition at the level of individual atoms, provide researchers with a means to trace particles back through billions of years of solar system history to the stellar environments where their constituent elements were first forged in the nuclear furnaces of dying stars. The analysis begins with isotopic signatures that immediately distinguish extraterrestrial material from any terrestrial source. Oxygen isotopes in cosmic dust particles often display ratios that differ dramatically from those found in Earth's rocks, atmosphere, and oceans, reflecting formation processes that occurred under conditions utterly unlike anything found on our planet. These oxygen isotope anomalies serve as unmistakable markers of extraterrestrial origin, allowing researchers to identify cosmic dust even when particles have been contaminated by terrestrial material during collection and processing. Carbon isotopes tell stories of organic chemistry that occurred in the vacuum of interstellar space, where molecular reactions proceed under conditions of extreme cold and virtually infinite dilution. Some cosmic dust particles contain carbon compounds with isotopic ratios that could only have formed through reactions involving molecular hydrogen and carbon monoxide on grain surfaces in dense interstellar clouds. These molecular fossils preserve evidence of the chemical processes that operated in the interstellar medium before the solar system formed, providing direct samples of the chemical evolution that preceded planetary formation. Silicon and magnesium isotopes reveal the high-temperature environments where refractory minerals first condensed from cooling stellar gases. Different types of stars produce distinctive isotopic signatures during nuclear synthesis, creating chemical fingerprints that can be used to identify the stellar sources of specific cosmic dust particles. Some grains display isotopic ratios consistent with formation in red giant star atmospheres, while others carry signatures of more exotic stellar environments, such as asymptotic giant branch stars or Wolf-Rayet stars, where extreme stellar winds create unique chemical conditions. The study of presolar grains embedded within cosmic dust particles has revolutionized understanding of stellar nuclear synthesis and galactic chemical evolution. These microscopic fossils formed around stars that completed their evolution before the Sun existed, preserve isotopic signatures that provide direct observational constraints on theoretical models of stellar interior processes. Each presolar grain represents a sample of matter that condensed in the atmosphere of a specific star and survived billions of years of cosmic wandering to eventually reach Earth's surface. Titanium isotopes in cosmic dust particles provide particularly sensitive indicators of nuclear synthetic processes that occurred in supernovae and other explosive stellar environments. The isotopic anomalies observed in some particles require formation in environments where nuclear reactions proceeded under conditions of extreme temperature and neutron flux that exist only during the most violent stellar events. These signatures provide direct evidence that some cosmic dust particles contain material that was processed through multiple generations of stellar evolution. Neon isotopes, trapped within cosmic dust particles, carry information about cosmic ray exposure during interplanetary transport, allowing researchers to estimate how long individual particles drifted through space before reaching Earth. The accumulation of cosmogenic neon isotopes occurs at rates that depend on cosmic ray flux and particle composition, creating chronometers that can measure exposure ages ranging from thousands to millions of years. These cosmic ray clocks provide constraints on particle orbital evolution and the dynamics of interplanetary transport. Advanced mass spectrometry techniques have revealed that individual cosmic dust particles often contain multiple isotopic populations that reflect complex formation and modification processes. Some particles display evidence of incomplete isotopic equilibration, preserving distinct chemical domains that formed under different conditions or at different times. These heterogeneous isotopic signatures provide insights into the physical processes that mixed materials from different stellar sources during the formation of the solar nebula. The isotopic composition of noble gases in cosmic dust particles provides information about solar wind implantation and cosmic ray interaction processes that occurred during interplanetary transport. Helium and argon isotopes display signatures that reflect both solar wind composition and nuclear reactions induced by cosmic ray bombardment. The relative abundances of different noble gas isotopes can be used to constrain exposure conditions and transport pathways in ways that complement information derived from other isotopic systems. Recent analytical advances have enabled researchers to measure isotopic ratios in particles containing only picograms of material, opening new possibilities for studying the rarest and most exotic cosmic dust samples. These ultra-sensitive techniques have revealed isotopic anomalies that were previously undetectable, including signatures that may reflect formation in interstellar environments with chemical compositions significantly different from the local galactic neighborhood where the solar system currently resides. The study of sulfur isotopes in cosmic dust particles has provided insights into nebular chemistry and early solar system processes that operated during planetary formation. Mass-independent sulfur isotope fractionation, observed in some particles, indicates formation under conditions where photochemical processes dominated over thermal equilibrium reactions. These signatures may reflect processing in the outer regions of the solar nebula, where ultraviolet radiation from nearby stars influence chemical evolution. Chromium isotopes in cosmic dust particles display variations that correlate with formation location within the solar nebula. providing constraints on the spatial distribution of different materials during the earliest phases of solar system evolution. Some particles contain chromium isotopic signatures that are consistent with formation in the inner solar nebula, while others display ratios that indicate origin in more distant regions where different chemical processes dominated material processing. The discovery of live radioactive isotopes in cosmic dust particles has provided direct evidence for recent nucleosynthetic events in the local galactic neighbourhood. Iron-60, with a half-life of several million years, has been detected in deep-sea sediments and attributed to supernova explosions that occurred within the past few million years in stellar associations relatively close to the solar system. These discoveries demonstrate that Earth continues to receive freshly synthesized stellar material from ongoing nucleosynthetic processes in nearby regions of the galaxy. Aluminum isotopes and refractory inclusions within cosmic dust particles preserve evidence of the earliest high-temperature processes that occurred during solar nebula evolution. The decay products of aluminum-26, a short-lived radioactive isotope that was incorporated into the earliest solar system materials, provide chronological constraints on the timing of planetary formation processes. These isotopic signatures help establish the temporal sequence of events that led from nebula collapse to planetary accretion. Laboratory studies of isotopic heterogeneity within individual cosmic dust particles have revealed fine-scale chemical structures that reflect mixing processes in stellar environments and subsequent modification during interplanetary transport. Some particles contain isotopic gradients that may record progressive chemical alteration during passage through different regions of interplanetary space. Others display isotopic zoning that preserves evidence of layered deposition processes that occurred in stellar atmospheres or circumstellar environments. Current research focuses on developing new analytical techniques capable of measuring isotopic ratios in ever smaller samples, potentially enabling isotopic analysis of individual mineral phases within cosmic dust particles. These advances may eventually permit reconstruction of detailed thermal and chemical histories for particles that experienced complex multi-stage evolution from stellar environments through interplanetary space to terrestrial collection sites. The isotopic signatures preserved in cosmic dust particles represent a form of cosmic archaeology that provides direct access to materials and processes that operated throughout the history of stellar evolution in the local galaxy. Each isotopic ratio tells part of a story that spans from the nuclear fires of stellar cores to the gentle accumulation of cosmic debris on planetary surfaces, creating a record of cosmic chemical evolution written in the language of atomic nuclei across the vast scales of space and time, in the precise measurements of atomic ratios that differ by fractions of a percent. Researchers read the signatures of stellar furnaces that burned billions of years ago. Chemical reactions that occurred in the frigid vacuum between stars, and transport processes that carried these microscopic messengers across interplanetary distances to preserve samples of cosmic history in terrestrial laboratories. Only took the universe billions of years to develop a cosmic postal system capable of delivering samples of stellar nucleosynthesis to planetary surfaces, and still the delivery continues, particle by particle, carrying isotopic messages written in the nuclear alphabet of stellar evolution across the astronomical distances between stars and worlds. In the vast space between planets, where the solar wind streams outward from the sun's corona at velocities exceeding 1 million kilometers per hour, cosmic dust particles experience a continuous process of modification and sculpting that operates over millions of years to alter their surfaces, compositions, and internal structures. This endless flow of charged particles, carrying with it the magnetic field lines that thread through interplanetary space, subjects every grain of cosmic dust to bombardment by protons, helium nuclei, and heavier ions that have been accelerated to energies measured in thousands of electron volts. The solar wind represents one of the most pervasive environmental factors in the solar system. a particle flux so intense that it delivers more than 10 to the 8th protons per square centimetre to any surface exposed to interplanetary space every second. For cosmic dust grains, with their high surface area to mass ratios and residence times measured in millions of years, this bombardment accumulates into a profound modification process that can alter particle properties in ways that have no terrestrial analogue. The implantation of solar wind ions creates chemical and structural changes that extend tens of nanometers into particle surfaces, creating altered layers that preserve records of the interplanetary environment encountered during cosmic transport. The process begins when high-energy protons and helium nuclei, accelerated by magnetic reconnection events in the solar corona, encounter cosmic dust surfaces with sufficient energy to penetrate crystal lattices and displace atoms from their normal positions. This ion implantation process creates amorphous surface layers where crystalline order has been destroyed by radiation damage, fundamentally altering the optical and chemical properties of affected materials. Simultaneously, the implanted solar wind ions become trapped within the particle structure, creating reservoirs of noble gases that carry isotopic signatures characteristic of the contemporary solar composition. Laboratory simulations of solar wind bombardment, conducted using ion accelerators that reproduce the energy and flux conditions found in interplanetary space, have revealed the remarkable efficiency with which this process modifies particle surfaces. Even relatively brief exposures, equivalent to cosmic transport times of thousands of years, can create detectable changes in surface chemistry and crystal structure. Longer exposures, corresponding to the million-year timescales typical of cosmic dust orbital evolution, produce modifications that extend through significant fractions of particle volumes. The solar wind flux varies systematically with distance from the Sun, creating gradients in modification intensity that depend on the orbital characteristics of individual particles. Grains that spend more time in the inner solar system, where solar wind density reaches its highest values, experience more intense bombardment than those that remain in the outer regions, where particle fluxes decrease with the square of solar distance. This creates a natural experiment in space weathering that allows researchers to correlate particle modification with orbital history and transport pathways. The chemical composition of solar wind varies with solar activity cycles and magnetic field configurations, creating temporal variations in the modification process that may be preserved in the layered structure of heavily bombarded particles. During periods of high solar activity, the solar wind becomes enriched in heavier elements and achieves higher velocities, potentially creating modification signatures that differ from those produced during quiet solar periods. These variations may eventually provide chronological information about solar activity levels during different epochs of cosmic dust transport. Recent spacecraft measurements of solar wind composition and flux in different regions of the solar system have revealed additional complexity in the bombardment environment experienced by cosmic dust particles. The interaction between solar wind and planetary magnetospheres creates regions of enhanced or depleted particle flux that may influence cosmic dust modification in ways that depend on particle orbital characteristics. Some regions of interplanetary space experience focus solar wind streams that create locally enhanced bombardment conditions. The magnetic field carried by the solar wind creates electromagnetic forces that can influence cosmic dust trajectories, particularly for particles that have acquired electric charges through photoelectric effects or previous bombardment events. These electromagnetic interactions add another layer of complexity to particle orbital evolution, potentially affecting the duration and intensity of solar wind exposure experienced by individual grains during their cosmic journeys. Advanced analytical techniques applied to collected cosmic dust samples have revealed solar wind modification signatures that provide detailed information about interplanetary transport conditions. Noble gas isotopic ratios in particle samples can be used to estimate exposure duration and solar wind flux intensity. Surface amorphization patterns observed through transmission electron microscopy reveal details about bombardment, geometry and energy distribution that constrain particle orientation and tumbling behavior during interplanetary transport. The discovery of solar wind-implanted hydrogen in cosmic dust particles has provided insights into water formation processes that may operate on grain surfaces in interplanetary space. When solar wind protons encounter oxygen-bearing minerals in particle surfaces, they can combine to form water molecules or hydroxyl groups that may be preserved within modified surface layers. These findings suggest that cosmic dust particles may serve as factories for water production in environments where liquid water could never exist. Comparative studies of solar wind modification in particles from different collection sites have revealed systematic variations that may reflect temporal changes in solar wind properties or spatial variations in the interplanetary bombardment environment. Particles collected during different solar activity cycles show subtle but measurable differences in modification signatures, suggesting that the solar wind sculpting process preserves records of solar variability over the timescales of cosmic dust transport. The interaction between solar wind bombardment and cosmic ray exposure creates complex modification patterns that reflect the multiple radiation environments encountered by particles during their cosmic journeys. While solar wind produces relatively shallow surface modifications, cosmic rays can penetrate much deeper into particle interiors, creating complementary records of different aspects of the interplanetary radiation environment. The combination of these effects produces modification signatures that carry information about both local solar wind conditions and galactic cosmic ray flux. Theoretical models of solar wind interaction with cosmic dust have revealed that the modification process exhibits strong dependencies on particle composition, crystal structure, and surface geometry. Particles composed of different minerals experience different rates and patterns of modification under identical bombardment conditions. This selective modification process may contribute to the chemical fractionation observed in cosmic dust populations, as different materials respond differently to prolonged solar wind exposure. The study of solar wind modification has implications beyond cosmic dust research, providing insights into space weathering processes that operate on airless planetary surfaces throughout the solar system. The modification signatures observed in cosmic dust particles serve as analogues for understanding how solar wind bombardment affects the surfaces of the Moon, asteroids, and other bodies that lack protective atmospheres. These studies contribute to interpretation of remote sensing observations and planning for future sample return missions. Current research focuses on understanding how solar wind modification efficiency has changed throughout solar system history as solar luminosity and magnetic field strength have evolved. During the early solar system, when the young sun may have been more magnetically active and produced enhanced solar wind fluxes, cosmic dust modification rates may have been significantly higher than contemporary values. These historical variations in modification intensity may be preserved in the most ancient cosmic dust samples. The development of increasingly sophisticated ion beam facilities has enabled researchers to conduct controlled experiments that reproduce specific aspects of solar wind modification under laboratory conditions. These experiments reveal details about modification mechanisms that cannot be observed directly in space, providing fundamental understanding of the physical and chemical processes that sculpture cosmic dust surfaces during their million-year journeys through the interplanetary medium. In the ceaseless flow of the solar wind, where charged particles stream outward from our star-carrying magnetic field lines and solar memories across the vast emptiness between worlds, cosmic dust grains undergo their patient transformation, accumulating layer by layer the chemical signatures of stellar breath and interplanetary weather. Each surface modification records another moment in the long conversation between particle and plasma, grain and field, creating microscopic archives of space environment conditions that operated long before instruments existed to measure them directly. only took the solar wind billions of years to perfect a sculpting process that works atom by atom across cosmic distances. And still the endless stream flows outward, carrying the sun's influence to the edge of interstellar space, writing its signature on every grain of dust that dares to wander in the light, in the most unlikely of places, scattered across urban rooftops and collected in the mundane drainage systems of cities around the world. Cosmic visitors accumulate with the same quiet persistence that characterizes their accumulation everywhere else on Earth's surface. These extraterrestrial particles, having completed journeys measured in millions of years and astronomical units, come to rest finally among decidedly terrestrial debris in environments that seem utterly removed from the cosmic processes that created them. Yet even in the heart of metropolitan areas, where human activity dominates every aspect of the local environment, the ancient rain of cosmic dust continues unabated, adding its microscopic contribution to the sediments that gather in rain gutters. On building surfaces, and in the corners where urban architecture meets sky, the discovery of cosmic dust in urban environments initially surprised researchers, who assumed that the overwhelming abundance of terrestrial contamination would make it impossible to identify extraterrestrial particles in such settings. However, careful chemical analysis of urban sediments has revealed that cosmic dust comprises a measurable fraction of the fine particulate matter that accumulates on city surfaces, typically ranging from less than 1% to several percent depending on local conditions and the efficiency of terrestrial particle removal processes. The collection process in urban environments operates through the same mechanisms that concentrate cosmic dust in more pristine settings, but with the added complexity of human infrastructure that can either enhance or inhibit particle accumulation. Building rooftops, particularly those with complex architectural features that can trap fine particles, often accumulate cosmic dust at rates comparable to those observed in remote locations. Rain gutters and downspouts act as natural concentrators, channeling particle-laden runoff into localized collection points where cosmic dust can reach concentrations sufficient for easy identification and analysis. Laboratory studies of urban cosmic dust have revealed that particles collected from city environments retain their essential extraterrestrial characteristics despite exposure to urban atmospheric chemistry and potential contamination from industrial sources. The distinctive isotopic signatures that mark extraterrestrial origin remain clearly detectable even in particles that have been exposed to urban pollution for extended periods. This resilience reflects the refractory nature of most cosmic dust compositions, which remain chemically stable under the range of conditions encountered in terrestrial urban environments. The size distribution of cosmic dust in urban collections differs subtly from that observed in more remote locations, reflecting the preferential removal of larger particles by atmospheric transport processes and the enhanced retention of smaller grains by urban surface features. Buildings and other structures create complex aerodynamic environments that can affect particle settling patterns, potentially concentrating certain size fractions while dispersing others. These urban collection effects must be considered when interpreting particle size distributions and using them to infer properties of the original cosmic dust population. Recent surveys of cosmic dust abundance in urban environments have revealed systematic variations that correlate with local topography, building density, and prevailing wind patterns. Cities located in valleys or other topographically enclosed settings may experience enhanced cosmic dust accumulation due to reduced atmospheric mixing and longer particle residence times. Urban areas with significant industrial activity show more complex particle signatures that require careful analytical work to separate cosmic contributions from terrestrial contamination sources. The chemical composition of urban cosmic dust provides insights into modification processes that may occur during extended exposure to polluted urban atmospheres. Some particles show evidence of surface alteration caused by reaction with atmospheric acids or other urban pollutants, creating modified surface layers that preserve records of urban atmospheric chemistry. However, these surface modifications typically affect only the outermost few nanometers of particle surfaces, leaving the bulk composition and structure essentially unchanged. Advanced analytical techniques capable of identifying individual cosmic dust particles within complex mixtures of urban debris have revolutionized the study of extraterrestrial material in anthropogenic environments. Secondary ion mass spectrometry and electron microscopy can distinguish cosmic dust from terrestrial particles, even when extraterrestrial material comprises less than 1% of the total sample. These capabilities have enabled systematic surveys of cosmic dust distribution in urban environments that would have been impossible using earlier analytical methods. The seasonal variations in cosmic dust accumulation observed in urban environments mirror those found in more pristine settings, confirming that urban collection sites preserve reliable records of temporal variations in extraterrestrial material flux during certain times of year, when Earth's orbital motion carries it through regions of enhanced cosmic dust density. Urban accumulation rates increase measurably. These seasonal patterns provide independent confirmation of cosmic dust flux variations derived from other collection methods. The study of cosmic dust in urban environments has revealed unexpected connections between extraterrestrial material delivery and local atmospheric processes. The fine particle size of cosmic dust allows it to serve as condensation nuclei for atmospheric moisture, potentially influencing local cloud formation and precipitation patterns in ways that may be detectable through careful meteorological analysis. While these effects remain subtle, they demonstrate that cosmic dust delivery can influence terrestrial processes even in highly modified urban environments. Citizen science projects focused on cosmic dust collection in urban areas have engaged amateur researchers in the systematic search for extraterrestrial particles in everyday urban environments. These projects have demonstrated that meaningful cosmic dust research can be conducted using relatively simple collection and concentration techniques, provided that appropriate analytical methods are available for particle identification and characterization. The results have contributed to broader understanding of cosmic dust distribution patterns and temporal variations. The preservation of cosmic dust in urban archaeological contexts provides opportunities to study historical variations in extraterrestrial material flux over timescales that bridge the gap between direct observation and geological records. Particles preserved in building materials, urban sediment layers, and other anthropogenic deposits may eventually provide records of cosmic dust accumulation during specific historical periods, creating archives that complement those found in natural sedimentary environments. Recent research has focused on understanding how urban heat island effects and atmospheric chemistry modifications may influence cosmic dust preservation and modification in city environments. Elevated temperatures and altered atmospheric composition in urban areas may affect particle stability and chemical evolution in ways that differ from those operating in rural or pristine environments. These urban modification processes may create distinctive signatures that can be used to trace cosmic dust transport pathways and residence times in anthropogenic environments. The discovery of cosmic dust in urban environments has implications for understanding particle cycling and transport processes in the global atmosphere. Urban areas represent significant sources of atmospheric particulate matter, and the cosmic dust component of urban aerosols may contribute to regional and global patterns of atmospheric chemistry and cloud physics. Understanding these contributions requires careful quantification of cosmic dust abundance in urban particle populations and assessment of how urban processes modify particle properties. Advanced computer models of urban atmospheric dynamics have begun to incorporate cosmic dust as a component of urban particle populations, revealing that extraterrestrial material may influence atmospheric processes in urban environments in ways that have not been previously recognized. These models suggest that cosmic dust may serve as particularly effective ice nuclei in urban atmospheres, potentially affecting precipitation patterns and storm development in ways that scale with cosmic dust flux variations. The integration of cosmic dust studies with urban environmental monitoring programs has created new opportunities to assess the health and environmental implications of extraterrestrial particle exposure in densely populated areas. While cosmic dust particles are typically too large to penetrate deeply into human respiratory systems, their chemical compositions and surface properties may have implications for understanding atmospheric chemistry and air quality in urban environments. In the bustling complexity of urban environments, where human activity seems to dominate every aspect of the local landscape, the ancient rain of cosmic dust continues its patient accumulation in rain gutters and on rooftops, adding microscopic samples of interplanetary matter to the debris of human civilization. Each particle carries within its structure the same cosmic memories and stellar heritage that characterize cosmic dust everywhere, creating unexpected connections between urban infrastructure and cosmic processes that operate across astronomical scales of space and time. Only took cosmic dust billions of years to learn that cities make adequate collection points for sampling infinity. And still the urban accumulation continues, gathering cosmic treasures in the most mundane corners of human habitation, writing cosmic poetry in the language of metropolitan sediment and starlight. The process that brings microscopic cosmic visitors to Earth's surface has operated with remarkable consistency throughout the vast expanse of geological time, creating one of the longest-running experiments in planetary science. For nearly 4.5 billion years, since the first stable oceans formed and the earliest atmosphere achieved something resembling its modern composition, our planet has served as a collecting surface for materials produced throughout the solar system and beyond. This cosmic conveyor belt has delivered samples of asteroid interiors, comet nuclei, and even interstellar space to Earth's surface with the reliability of a geological clock, accumulating layer by layer a record of cosmic evolution that spans the entire history of the solar system. Current estimates suggest that Earth's mass increases by approximately 40,000 tons each year through the accumulation of cosmic dust and larger meteoritic material, a growth rate so modest that it would require billions of years to produce measurable changes in planetary characteristics, yet significant enough to have delivered substantial quantities of extraterrestrial matter over geological time. When integrated across Earth's entire history, this cosmic accretion may have contributed several hundredths of a percent to the planet's total mass, while providing much larger relative contributions to the atmospheric inventory of rare gases and certain trace elements that occur in cosmic materials at concentrations far exceeding their terrestrial abundances. The mathematical precision of this delivery system emerges from the orbital mechanics that govern the motion of dust particles throughout the solar system. While individual particle trajectories exhibit chaotic complexity due to the influence of radiation pressure, gravitational perturbations, and electromagnetic forces, statistical populations of particles follow predictable evolutionary pathways that can be modelled using the same mathematical frameworks that describe planetary orbital motion. These models reveal that the cosmic dust environment exists in a state of dynamic equilibrium, where particle production through asteroid collisions and comet outgassing balances particle removal through Poynting-Robertson, drag, and atmospheric capture. The delivery process exhibits remarkable efficiency in transporting materials from the most distant regions of the solar system to planetary surfaces in the inner system. Computer simulations suggest that particles originating in the Kuiper Belt or Oort cloud can reach Earth-crossing orbits within timescales that are short compared to solar system age, creating opportunities for direct sampling of materials that formed under conditions utterly unlike those found in the inner solar system. This cosmic sample return system operates continuously without mechanical failure or technological obsolescence, providing access to materials that no conceivable space mission could retrieve directly. Recent discoveries in the field of astrobiology have highlighted the potential importance of cosmic dust delivery for the origin and early evolution of life on Earth. Many cosmic dust particles contain organic compounds that formed through chemical processes in interstellar space, including amino acids, polycyclic aromatic hydrocarbons, and other molecules that may have served as precursors to biological chemistry. The continuous delivery of these organic materials throughout Earth's history may have provided a steady supply of chemical building blocks that supplemented local organic synthesis and contributed to the chemical evolution that eventually led to living systems. Laboratory studies of organic compounds in cosmic dust particles have revealed molecular structures that could not have formed under terrestrial conditions, including complex carbon chains that require the extreme cold and long reaction times available only in interstellar environments. These molecules preserve records of chemical evolution that occurred before the solar system formed, providing insights into the prebiotic chemistry that may have influenced the emergence of life throughout the galaxy. The delivery of such materials to planetary surfaces represents a form of cosmic chemistry that connects stellar evolution to biological evolution across astronomical scales of space and time. The isotopic signatures preserved in cosmic dust particles provide chronological information about the delivery process itself, revealing how cosmic dust flux has varied throughout Earth's history in response to changes in solar system dynamics. Periods of enhanced dust delivery correlate with major disruptions in the asteroid belt, close approaches of large comets, and the gravitational influences of migrating planets. These flux variations may have influenced Earth's atmospheric evolution, climate history, and biological development in ways that are only beginning to be understood. The cumulative effects of cosmic dust delivery over geological time may have played significant roles in shaping Earth's atmospheric composition and chemistry. Noble gases delivered by cosmic dust exhibit isotopic ratios that differ from those in Earth's mantle, suggesting that atmospheric noble gas inventories may have been significantly influenced by cosmic accretion. Similarly, certain trace elements that are rare in Earth's crust but abundant in cosmic materials may owe their surface concentrations to billions of years of extraterrestrial delivery. Advanced computer models of cosmic dust delivery throughout solar system history reveal that the efficiency and composition of the delivery process have evolved significantly as planetary configurations have changed and the cosmic dust environment has matured. During the late heavy bombardment, approximately 4 billion years ago, cosmic dust delivery rates may have been orders of magnitude higher than contemporary values, potentially delivering substantial amounts of extraterrestrial organic matter to Earth's surface during the crucial period when life was first emerging. The global distribution of cosmic dust delivery exhibits subtle but measurable variations that reflect atmospheric circulation patterns and the three-dimensional structure of Earth's gravitational field. Polar regions, where atmospheric circulation creates enhanced settling efficiency for fine particles, may receive cosmic dust at rates slightly higher than tropical regions. These geographic variations in delivery efficiency may have influenced regional patterns of trace element cycling and atmospheric chemistry throughout Earth's history. Recent research has focused on understanding how cosmic dust delivery rates have responded to periodic variations in solar system architecture, including the orbital cycles of giant planets and long-term changes in asteroid belt structure. These astronomical forcing mechanisms may have created periodic variations in cosmic dust flux that operated over timescales ranging from thousands to millions of years, potentially influencing Earth's climate and atmospheric chemistry in ways that may be detectable in geological records. The study of cosmic dust delivery has revealed unexpected connections between astronomical processes and terrestrial biogeochemical cycles, certain trace elements delivered by cosmic dust, including osmium, iridium, and platinum group elements, exhibit distinctive isotopic signatures that allow their cosmic origin to be traced through Earth's geochemical systems. These cosmic traces provide unique opportunities to study global element cycling and the connections between atmospheric chemistry and biological processes. Current estimates of cosmic dust delivery efficiency suggest that Earth intercepts only a tiny fraction of the cosmic dust produced throughout the solar system, with most particles either spiraling into the Sun or being ejected to interstellar space by radiation pressure and gravitational perturbations. However, the small fraction that does reach Earth's surface provides a remarkably representative sample of solar system materials, including representatives of virtually every major class of extraterrestrial matter, from comets to asteroids to interstellar grains. The future evolution of cosmic dust delivery will be influenced by long-term changes in solar luminosity, planetary orbital evolution, and the gradual depletion of small body populations throughout the solar system. As the Sun brightens with age, increased radiation pressure may reduce the efficiency of cosmic dust delivery to the inner planets. Simultaneously, the continuing depletion of asteroid belt and Kuiper belt populations may reduce overall dust production rates, gradually decreasing the flux of extraterrestrial materials reaching planetary surfaces. The technical challenges of studying cosmic dust delivery have driven the development of analytical techniques that push the boundaries of measurement science. The ability to determine complete chemical and isotopic compositions of individual particles weighing less than a nanogram represents one of the most remarkable achievements in analytical chemistry, enabling detailed study of cosmic processes or examination of samples so small they approach the theoretical limits of matter organization. In the patient accumulation of cosmic particles on planetary surfaces, grain by grain and year by year across the vast scales of geological time, the universe demonstrates its capacity for precision engineering on cosmic scales. The delivery system operates with the reliability of stellar mechanics and the gentleness of atmospheric physics, ensuring that samples of cosmic evolution reach terrestrial laboratories where they can be studied by observers who evolved on a world built partially from the same cosmic materials that continue to arrive each day from the depths of space. Only took the solar system 4 billion years to establish a sample return program that operates automatically across astronomical distances. And still the cosmic conveyor belt continues its ancient work, carrying messages written in stardust across the immeasurable gulf between worlds, delivering infinity one particle at a time to a planet patient enough to catch samples of eternity as they fall. As darkness spreads across the continents and artificial lights begin to dot the landscape below, marking the transition from day to night that has repeated itself billions of times since Earth first began spinning in the light of the young sun. The invisible rain continues its ancient descent through the cooling air, high above the aircraft that trace their paths between cities. Beyond the reach of weather and the influence of seasons, microscopic travellers complete journeys that began when continents occupied different positions, and life on Earth took forms that would be unrecognisable to contemporary observers. Each particle that settles through the night air carries within its crystalline structure a unique story of cosmic wandering, a molecular autobiography written in isotopic ratios and mineral assemblages that record environments extending from the cores of distant stars to the frozen darkness beyond the planets. Some grains preserve evidence of formation in stellar atmospheres that achieved temperatures exceeding those found in terrestrial nuclear reactors. Others display chemical signatures of the interstellar medium, where molecular reactions proceed at temperatures approaching absolute zero over timescales that encompass the rise and fall of entire stellar generations. The mathematics of this cosmic precipitation reveal processes operating with clockwork precision across scales that challenge human comprehension. Orbital mechanics determine particle trajectories with the same fundamental accuracy that governs planetary motion, while electromagnetic forces and radiation pressure modify these paths according to physical laws that have remained constant since the universe learned to organize matter into stars and worlds. The resulting particle flux exhibits variations that correlate with Earth's orbital position, solar activity cycles, and the passage of the solar system through different regions of interstellar space. Current estimates suggest that somewhere between 15 and 300 tons of this extraterrestrial material settle onto Earth's surface each day, a range of uncertainty that reflects the fundamental challenges of measuring phenomena that operate at the intersection of the infinitesimal and the astronomical. The actual mass accumulation probably varies significantly with solar activity, comet passages, and Earth's encounter with debris streams left behind by ancient cosmic visitors. These variations create natural experiments in cosmic dust delivery that may eventually provide insights into solar system evolution and the dynamics of interplanetary space. The real-time nature of this process means that particles settling through tonight's atmosphere include grains that began their earthward journey during different epochs of Earth's history. Some started their migration when the first complex cells were learning to harvest sunlight through photosynthesis. Others commenced their orbital decay when the first animals were developing the neural complexity that would eventually lead to consciousness capable of recognizing their cosmic origin. A few may have initiated their inward spiral before life existed at all, drifting through space for billions of years while continents assembled and oceans formed around a planet that was still learning how to organize itself into the complex chemical systems that would eventually support observers capable of understanding their meaning. The chemistry preserved within these falling particles spans the entire periodic table of elements, from hydrogen formed in the first moments after the Big Bang to uranium forged in supernova explosions that scattered stellar debris across light years of space before gravity collected some of these atoms into the rocky materials that would eventually become cosmic dust. Each element carries its own story of nuclear evolution, stellar processing, and chemical combination under conditions that range from the extreme temperatures of stellar cores to the near absolute zero environments of interstellar clouds. Laboratory analysis reveals that many particles contain multiple generations of stellar material. Microscopic archaeological sites where pre-solar grains preserve samples of individual stars embedded within matrices that formed during solar system evolution. These nested structures create Russian dolls of cosmic history, where materials from different stellar sources and different epochs of galactic evolution have been combined through processes that operated over billions of years to create single particles smaller than bacteria, yet more complex than any human technology. The organic chemistry embedded within cosmic dust particles tells stories of molecular evolution that occurred entirely in the vacuum of space, where chemical reactions proceed according to rules that have no terrestrial analogue. Complex carbon compounds formed through surface reactions on grain surfaces in dense molecular clouds, amino acids synthesized through radiation-driven chemistry in interstellar space, and polycyclic aromatic hydrocarbons created in the atmospheres of carbon-rich stars all contribute to a cosmic biochemistry that may have provided some of the molecular building blocks from which terrestrial life eventually emerged. Recent discoveries suggest that some particles contain water ice and other volatile compounds that survive the journey through interplanetary space despite millions of years of exposure to solar radiation and cosmic bombardment. These cosmic refrigerators preserve samples of the ice that existed in the outer regions of the solar nebula when planets were first accreting from disk materials, providing direct access to the chemical conditions that existed during the earliest phases of planetary formation. The continuing accumulation of this cosmic material ensures that Earth's chemical inventory continues to evolve, albeit at rates so slow they are measurable only through geological processes that integrate changes over millions of years. Certain trace elements that are rare in Earth's crust but abundant in cosmic materials may owe their surface concentrations primarily to billions of years of extraterrestrial delivery. The isotopic composition of Earth's atmosphere shows clear evidence of cosmic contributions, particularly in the noble gas inventory that preserves signatures of solar wind implantation and cosmic ray interactions that occurred during interplanetary transport. The global nature of cosmic dust delivery means that every square meter of Earth's surface receives its share of extraterrestrial visitors, creating a planetary-scale sampling program that operates continuously without geographic bias or temporal interruption. Remote islands in the middle of oceans collect the same cosmic materials as continental interiors. Antarctic ice sheets preserve cosmic dust with the same efficiency as tropical rainforests. Urban rooftops accumulate extraterrestrial particles alongside the debris of human civilization, creating unexpected juxtapositions of cosmic and terrestrial materials in the most anthropogenic environments. The technical achievement represented by cosmic dust research demonstrates the remarkable progress in analytical chemistry that has occurred over the past several decades. The ability to determine complete chemical and isotopic compositions of individual particles weighing less than a trillionth of a gram represents one of the most sophisticated measurement capabilities ever developed, pushing analytical techniques to the fundamental limits imposed by atomic structure and quantum mechanics. These capabilities enable detailed study of cosmic processes through examination of samples so small they exist at the boundary between individual molecules and measurable quantities of matter. Future developments in analytical technology may eventually enable real-time analysis of cosmic dust as it settles through the atmosphere, creating continuous monitoring systems that could detect variations in cosmic dust flux with temporal resolution measured in days rather than years. Such capabilities would provide unprecedented insights into the dynamics of the cosmic dust environment and its response to astronomical events such as comet passages, solar activity variations, and the solar system's motion through different regions of interstellar space. The philosophical implications of cosmic dust research extend beyond planetary science to questions about the fundamental connectedness of matter throughout the universe. The continuous delivery of cosmic materials to planetary surfaces creates physical links between astronomical and terrestrial processes that operate across scales ranging from atomic to galactic. Every breath contains atoms that once drifted free in interstellar space. Every handful of soil contains fragments of asteroids and comets that preserve chemical signatures from the earliest epochs of solar system evolution. The study of cosmic dust has revealed that the boundary between terrestrial and extraterrestrial matter is far less distinct than once supposed. The chemical elements that compose living organisms, the rare earth metals that enable modern technology, and the noble gases that provide chronological information about Earth's atmospheric evolution all show evidence of cosmic contributions that reflect billions of years of material exchange between Earth and the broader solar system. Current research continues to reveal new aspects of cosmic dust delivery and its implications for understanding Earth as part of a larger cosmic system. The discovery of cosmic dust particles with unusual isotopic signatures suggests that Earth occasionally receives materials from stellar sources beyond the local solar system, providing direct samples of galactic chemical evolution. The identification of organic compounds in cosmic dust that could not have formed under terrestrial conditions offers insights into the chemical complexity that exists throughout the universe and may have contributed to the emergence of life on Earth and potentially elsewhere. The precision with which cosmic dust particles preserve records of their cosmic journeys creates opportunities to study astronomical processes that operate over timescales far longer than human observation. Individual particles serve as natural spacecraft that have sampled conditions throughout the solar system over millions of years, returning to Earth with information about radiation environments, magnetic field configurations, and chemical compositions that existed long before instruments were available to measure them directly. The continuing evolution of cosmic dust research promises to reveal ever more detailed information about the connections between stellar evolution, planetary formation, and the chemical processes that led to life on Earth. Advanced analytical techniques under development may eventually enable researchers to trace individual cosmic dust particles back to their specific stellar or cometary sources, creating detailed maps of matter transport throughout the local galaxy and providing direct observational constraints on models of stellar nuclear synthesis and galactic chemical evolution. In the quiet darkness that settles over Earth as each day transitions to night, the ancient rain continues its patient descent, adding microscopic samples of cosmic evolution to a world that has been accumulating evidence of its astronomical heritage since the first atmosphere formed around a young planet, learning to dance in the light of a newly ignited star. Each particle carries within its structure the memory of stellar furnaces and interstellar wandering. The chemical signatures of processes that operated before Earth existed and will continue long after our planet has completed its own stellar evolution. The accumulation continues in perfect silence, grain by grain and night by night, writing the longest story ever told in the patient language of atomic nuclei and crystal structures. Right now, as these words are read, thousands of cosmic visitors complete their million-year journeys, settling onto surfaces around the world with the same gentle inevitability that has characterized this process since the beginning of planetary time. Only took the universe billions of years to establish a cosmic library delivered one particle at a time to a world capable of reading the stories written in stardust and preserved in the accumulated sediments of deep time. And still the quiet accumulation continues, adding its ancient treasures to a planetary archive that grows more comprehensive with each passing moment, each falling grain, each microscopic messenger that carries samples of infinity across the astronomical distances between birth and rest, between stellar cores and planetary dreams, between the fires of creation and the gentle silence of cosmic dust settling through terrestrial darkness toward a surface patient enough to catch fragments of eternity as they fall. The ancient rhythm slows now, as it has slowed countless times before, across the vast expanse of geological ages, somewhere high above the sleeping world. The last particles of tonight's cosmic rain drift through increasingly dense layers of atmosphere, their million-year journeys finally approaching completion. Each grain settles with the weight of accumulated starlight, carrying samples of distant suns toward a planet that has grown accustomed to receiving gifts from the darkness between worlds in laboratory freezers around the globe. Cosmic dust particles wait in pristine silence for instruments sensitive enough to read the stories written in their atomic structures. Some preserve the chemical signatures of red giant stars that exhausted their nuclear fuel before Earth learned to dream in stone and water. Others contain organic molecules that formed in interstellar clouds so vast they dwarf entire solar systems. Chemical complexity born in the cosmic cold and delivered across astronomical distances to rest finally in terrestrial archives. The process continues without fanfare or ceremony, as it always has, as it always will. Tomorrow's dawn will illuminate a world slightly heavier than it was the night before, enriched by the microscopic addition of materials that travelled farther than any human explorer, older than any terrestrial mountain, carrying within their crystal matrices the accumulated memory of cosmic evolution, written in the universal language of nuclear fusion and gravitational collapse. In the deepest silence of the cosmic night, where particles drift between stars and time moves with the patience of geological ages, the invisible rain falls still, adding its immeasurable gifts to a world that has learned to catch samples of infinity as they settle through darkness toward the patient surface of a planet built partially from stardust, partially from dreams, entirely from the slow accumulation of cosmic matter across the immeasurable distances between birth and rest. Sleep well, Earth. Sleep well, cosmic wanderers. Sleep well, ancient rain.